Good morning, everyone. Thanks for waking up early, especially since we're going to talk Windows features. Uh, Credential Guard is one of the biggest changes Microsoft has done to their OS architecture as a whole and lately. And it's interesting on its own, but I think some of its ideas could eventually make their way into Linux and KVM, independent of Windows. So yeah, it's worth looking into it. On top of that, we really want to be able to run it on Windows guests, which is nice on its own. We really want to have some discussion, so I may rush through some of the slides, but that's the point of this anyway. And a quick introduction. I'm Nicholas. Anel here will share the presentation with me. We're kernel and hypervisor engineers at AWS. We build the Nitro hypervisor, which powers most of EC2. It's a set of custom user space components and Linux plus KVM, although we do have 1,000-ish downstream patches. It's a gap we're trying to close, and this is one of the examples. The line of work we do is essentially building a hypervisor that would do all the operations you expect from a cloud provider, so from configure and launching VMs, live migration, live update, but also running more esoteric workloads like GPUs, AI acceleration, overcommitted platforms, and confidential computing like SEV-SMP. All the work we are presenting here isn't strictly ours. The project was started by Evgeny Yakovlev, and it was later joined by other engineers. We're gonna introduce virtualization-based security, which is a Microsoft concept, and go slowly into what VSM really is, and Credential Guard as well. Then discuss the actual guest hypervisor interface, and finally discuss our upstreaming plans. So as we were talking with our colleagues here in the conference, we realized there's some confusion on how we might be running Hyper-V and Windows guests. A lot of people assume that we were doing nested virtualization, where KVM would launch the Hyper-V hypervisor at level 1 and then have a Windows guest as a nested level 2 guest. That's actually not the case. What we're doing is emulate Hyper-V in KVM and running the Windows guest as a level 1 guest. So yeah, it's important to have that clear. So let's talk some naming schemes Windows introduced. First of all, you'll see it all over the documentation, and it's important to see how it's layered. Virtualization-based security is a catch-all term to refer to all the technologies that rely on hypervisor to create isolated virtual environments, as well as harden the operating system. I'll give some concrete examples, but the core concept behind it is benefiting from the fact that would give more trust to the hypervisor than the guest operating system, and especially in the cloud computing world, but as well as the desktop world if you're running Windows. And you can leverage that extra protection boundary to implement features that further protect your operating system or secrets. Device Guard is an example of this. I'll give an overview, not very precise, but it'll give you an idea of what happens. It prevents untrusted code from running in Windows. What would happen is that Windows will ask the hypervisor to remap the whole system memory as non-executable, and only after verifying each one of the binaries in the system, it will ask again the hypervisor to remap those memory ranges as executable. So your attacker that has compromised the operating system won't be able to inject new binaries into your system as long as he hasn't compromised the hypervisor as well and the whole interface, VSM interface. Yeah, Credential Guard follows a similar approach, but it's meant to hide secrets from the kernel and also provides an interface to interact with the secrets in a way that the kernel will never really map them into its own memory. So again, Hyper-V will be asked to remap the memory ranges where these secrets are stored as non-accessible, and yeah, essentially an attacker won't be able to use them. Virtual Secure Mode, VSM, is what Microsoft defined, is the primitive that Microsoft defined to build these sort of features. And it's the core guest kernel to hypervisor hypercall interface and all the semantics, and it's defined in a spec. We refer to it as TLFS, and Microsoft publishes it. It's a best effort spec. It doesn't go all the way down, so there's some amount of reverse engineering involved when implementing all this, but it gives you a good idea of what you're meant to be doing. Actually, this talk should have been called Enabling Hyper-V Virtual Secure Mode in KVM, but we figured that mentioning Credential Guard would bring in more people in. Yeah. Some platform requirements. I'll be very fast here. Secure boot. This is essential to be able to trust your bootstrap. Otherwise, an attacker can just mess up with your booting setup and disable Credential Guard. A modern CPU, of course. UEFI lock, again, to avoid an attacker from disabling Credential Guard, and TPM. Now, Anel is going to start with an overview of VSM.
Yeah, so hi. Yeah, I'm going to give a quick introduction into VSM, introduce some of its core concepts, and then also give a few details on how we actually implemented it. So VSM, or Virtual Secure Mode, it provides a security boundary using virtual trust levels, or VTLs. VTLs are basically privilege levels. So they are hierarchical. The higher the VTL number, the more privileged it is. Hyper-V spec provides or defines up to 16 VTLs, but in practice, we've only seen VTL 0 and VTL 1 being used. Then VTL 0 would be the normal mode, and VTL 1 is the secure mode. VTLs are orthogonal to ring levels. So when you have two VTLs, you still have your kernel and user modes, but VTL1 kernel is different from the kernel that runs in normal mode, so it's a small, secure kernel. Yeah, and the basic idea is that even if your kernel in VTL0 is compromised, you still have another more privileged VTL1 that can protect secrets or prevent execution of unsigned binaries. So VTL is an attribute of a vCPU. So each vCPU always has one active VTL that it's running in, and then it can switch to a different VTL via either hypercall, or it can be forcibly switched into a different VTL via interrupt or intercepts. So for each CPU and each VTL, there are certain private registers and MSRs, but some registers and MSRs are shared between VTLs of the same vCPU. And finally, for each VTL, there are different memory access permissions. So that's how VTL1 protects or hides data from VTL0. And Microsoft implemented this for both x86 and ARM. But yeah, we implemented it for x86. So a similar analogy, an interesting analogy is to ARM Trust Zone. So you could think of VTL0 as normal world, VTL1 is the secure world, and then hypervisor would play the role of the secure monitor. How does VSM get enabled? So VSM could be enabled by, for example, setting up Credential Guard in your group policy, and then it will actually get activated on the next boot. So in a normal case, when Windows boots without VSM, you have your bootloader that loads the kernel of the normal mode and then launches the user space processes. But when you have VSM enabled, bootloader would find the UEFI variable that will tell that VSM is enabled. It will then load secure kernel. Secure kernel will go on enable VSM, jump into VTL1, bootstrap vCPUs, then launch the secure processes, for example, Credential Guard. Then, after it's done executing, secure kernel jumps back to VTL0, gives control back to the bootloader, and then the normal boot process continues. So yeah, as I mentioned, there are two ways a VTL switch can happen. So the first one is a synchronous one. That one is when guest actually asks to be switched into a different VTL. That happens via hypercalls. So a jump into a higher privileged VTL1 is VTL call, and then going back to a less privileged VTL0 is a VTL return. From the hypervisor perspective, the main thing here is just is to store the content, the private state of current VTL, load the context for the next VTL, and yeah, basically return, give control back to the guest. Yeah, I forgot to mention, so for each VTL, there is a private interrupt subsystem. So yeah, during VTL switch, you would also want to switch into correct APIC. VTL return from the hypervisor perspective is exactly the same. Restore the previous VTL, store the content of the previous VTL, and then jump into the next VTL. Yeah, and the second way the VTL switch can happen is when CPU is forcibly switched into a different VTL. That happens via interrupts. So two rules here. First, all interrupts are now targeting a VTL, and that is basically derived from the origin VTL of the interrupt. So that would be if CPU is running in VTL1, then the interrupt that it's sending is gonna target also VTL1. All external interrupts are targeting VTL0. And the second rule, VTL1 always has precedence over VTL0. So if CPU is running in VTL0 and the interrupt that gets injected is in VTL1, tagged with VTL1, that CPU is switched into VTL1 so that it can go and process that interrupt. When the opposite happens and CPU is running in VTL0, in VTL1 gets an interrupt of VTL0, that interrupt is saved, but it will only get processed when that CPU voluntarily issued a VTL return and went back into VTL0. Yeah, so some implementation details. So what we've done, we basically have extended the vCPU state to have multiple sets of those private registers and MSIs. And we did the same for APIC. So now each vCPU can have multiple APICs, one for each VTL. Yeah, and the main challenge that we've seen with this approach is that it's quite intrusive. It goes into core x86 vCPU code. So it was, and there are a lot of edge cases where you have to adjust for the fact that you have now like multiple APICs and multiple vCPU states. And second thing also for stuff like live migration, serialization and deserialization becomes more complex because you have to restore context for both active VTL at the time and the inactive VTL that CPU was not running in. And finally, my VTL protections, memory protections. So that's how VTL1 would hide data from VTL0 or how it would prevent execution of unsigned binaries. So CPU, depending on which VTL it's running in, would have different access permissions to memory. Otherwise, the GPA to host memory mapping is the same for both, except overlay pages. Yeah, so basically the biggest difference is just memory access permissions. So VTL1 can request hypervisor to revoke, read, write, or execute access. If hypervisor notices that VTL0 is trying to violate that access permission, hypervisor can inject an intercept and notify VTL1 of the violation. Yeah, and implementation. So first thing, what we've done is that we used separate address spaces for each VTL. In that way, you have a different set of memory slots for different VTLs. So that's how we achieved isolation between them. It also allows to do stuff like mapping overlay pages to different host memory for different VTLs. And that's a requirement for VSM. And the second thing, for the actual protection changes, we used memory slot wide access access permissions. So the read-only slots were already supported by KVM, and we've extended it with non-executable and also completely non-readable, non-accessible memory slots, and that allowed us to support the full set of required permissions. So what we would do is that, if you have like a big giant memory region and then there is a page in the middle that needs to be protected, we would remove that slot and replace it with 3 new ones, and then the one that was in the middle, then it gets a new permission. So now it's a protected region. So yeah, we quickly realized after implementing it that there are a few problems with this. So first, you need to either suspend VCP use while you're making this change, because you may get into this inconsistent state while you deleted one slot and then haven't fully replaced it with all the 3 new ones. So you either need to stop all VCP use, or you need to do this whole operation atomically. And that's what we've done. But still, even with this optimization, we saw that it's not very efficient because Windows makes like hundreds and thousands of those changes while booting. Another thing, of course, that you can see here, we're only interested in changing permissions for this small region in the middle. And instead, we're actually operating on this giant GPA range. To achieve a better performance here, we also introduced targeted zapping when doing that atomic slot update. And with this, I'll yield back to you.
So in terms of I/O accesses, there's a big rule. All I/O memory accesses happen in VTL 0. And this brings another set of problems because whenever VTL 1 decides some memory region is accessible to VTL 0, we have to reflect that in the IOMMU. And this happens during runtime and concurrent to other I/O. So IOMMU changes have to happen in a special way. They have to be atomic and always present a valid view of the I/O mappings. We also need to support being able to change the backing memory of an IOVA. And this is because we can't really deal with no access mappings in our hardware, because some of our DMA controllers can, upon getting a PCIe error, can't walk back and don't have the context to realize which virtual function triggered that PCIe error. And if you're running a cloud computing company, not being able to know which of your clients is trying to break DMA, it's a problem. So we're forced to shut down the whole PCI bus, and that's not acceptable. So what we're doing instead is, upon getting a non-access mapping, we redirect that IOVA onto a scratch page, which we know to be safe and won't contain client data. So yeah, it's another requirement to how we have to do IOMMU updates. What we did is introduce a new IOMMU driver callback that we call remap. It, again, atomically updates IOMMU mappings during runtime with all the requirements I mentioned. We implemented this for both Intel and AMD, and funnily enough, it's the only part of VSM that is vendor-specific. We also had to implement merging back into huge pages, because VSM has this pattern where it will protect a memory range, do some work, and unprotect it. So that was fragmenting page tables a lot, and this is hurtful in terms of memory consumption, but as well as if you're trying to do live migration, it's not ideal. And yeah, we expose everything through a VFIO IO control, nothing special about that, just going over the VM's IOMMU domains. So what are our plans for upstream? We first of all feel bad that we didn't have an RFC or something before this talk. So we published our work in progress code. It's very rough and insecure, and I wouldn't call that a full credential guard VSM implementation, but it's something, and it runs on a fully upstream virtualization stack. No, this is just, is this the implementation we already described or an upstream one? a better one. No, this is the downstream one, but we will be working iteratively and making it better. And I'll describe the work we're planning on doing. So, yeah.
The one that we shipped in EC2 obviously has the security features.
Oh,
lacking here.
No, my bad. Yeah.
Just chiming in.
This is a limited rebase of what we have, and it's a starting point. No, Alex did good here. Thanks. So yeah, we have three main challenges in terms of upstreaming VSM. First of all is finding a better way of managing VTL state. And I think it's pretty clear that the proper way of doing it would be having a struct vCPU per VTL and finding a way to map specific VTLs to specific guest CPUs. And that can be done easily through the EPIC-ID, the MP state, and the VTL marker we will introduce into the struct vCPU. VTL switching should be almost trivial because it's just switching, running another vCPU, and as well as serialization and deserialization, which comes for free. There's still some share state, and then there's also interrupt injection, which will bring in new code, but it should be way more concise than what we did earlier. Another thing we're planning to introduce is memory protections, and this will go on a second patch series, hopefully. We want to piggyback on the proposed memory attributes IO control that Intel wants to introduce for guest private memory. It pretty much does everything we need, so being able to change the protection on specific GPAs, and it's not bound to memory slots, so it's faster and simpler. The only problem we have with the current implementation is that we don't have a way to map specific memory attributes to specific VTLs. Historically, how we do things, we would add address space support, but maybe that doesn't really fit in the memory attributes abstraction. So it's something we would love to discuss. We could add some way to add extra ancillary data, or I don't know. I'm open to hear ideas. Otherwise, address spaces works for us perfectly. For IOMMU protections, our plan is to rebase that remap callback we introduced in the IOMMU drivers, feed that into IOMMUFD, and send an RFC independent. We have some other workloads that might benefit from this internally, so overcommitted platform and some live migration setups will benefit from having this sort of APIs, but I'm sure people from outside the cloud world can tell me more use cases for IOMMU remap operation. Okay, so that's pretty much it. I hope you have a better picture now of what VSM is, and we'll appreciate any comments, criticism, and suggestions. Thank you.
Hi, I have a question about the big picture. So in the beginning of your presentation, I think you had a slide showing Hyper-V is running. We're not just doing the Hyper-V enlightenments. Can you go back to that slide? So my question about that is basically, how do the concepts that you've introduced map to that diagram? For example, is the VTLs, it sounds like they're implemented in the KVM kernel module. Well, oh, hang on. I got it the wrong way around, right? So you're not doing Hyper-V in KVM.
This is bad. This is good.
Okay, so my next question was, is all of this stuff encapsulated inside the KVM kernel module, or is there stuff that goes out to user space and then a VMM needs to do some of it?
Some parts of it go into QEMU and the VMM, whichever you use, and some parts stay in the kernel. For example, interrupt management will be in the kernel, in KVM, sorry. Some higher level stuff can be handled in QEMU, especially right now, some memory management, memory protections have to go all the way to QEMU to then support stuff like live migration and so on. You need the user space to be aware of all the memory protections that are happening on the system.
Okay, thank you. That's what I was curious about.
couple of questions, not related to the implementation, but more about VTLs in general. So how often do VTL switches happen, and how slower is the right thing, like the right side, so wrong thing?
Nested, you mean?
Yes.
How often would you know, like a good number?
Most of it happens during boot when the whole VSM gets enabled, but then we also see that there are like a few VTL protection changes during runtime as well. And also, I mean, when we were doing the memory protections, we also did a few like measurements on like strictly around that. Yeah, most of that happens also during Windows updates. So there are some kind of probably set up for that, you know, secrets that want to be hidden. We haven't measured what would be the difference between using nested versus KVM enlightened Hyper-V, if that was your question.
As the other two mentioned, they joined the team slightly later. We did initially measure the overhead of the Hyper-V solution, and that was roughly, depending on your workload, somewhere between 10 and 15% compared to not doing VSM. Obviously, doing VSM always has an overhead, regardless of what you do. But in normal operation, it's close to free because you do like, I don't know, 10 or so enters to VTL1 during normal operation.
So basically 10%.
Second?
10%.
So Hyper-V gives you a 10% overhead. Yeah, that's the right-hand side.
Yeah, thank you.
I'm not sure if there is a use case for something like nested credential guard, but does your work here potentially enable that if it were to be implemented?
I'm not sure what do you mean by
So imagine you have a credential guard VM that wants to run a VM. I don't know if there's a use case for that, but I mean, it seems like, you know, since it's third level nesting.
Okay. I'm not sure it would even be possible nor secure to begin with. Or maybe no, I don't think that's the idea behind it. What we know can happen is that for some nested setups you have an extra VTL level, which is something we just discovered and it's not publicly announced. But that's another story. Yeah, so no, you wouldn't be doing that inside the secure world.
Mm-hmm. Thanks.
Thank you. Okay, well, I guess that's all. Thank you very much.
All right, there's a few more people coming in, but I'm going to get started because this talk fills half an hour. Alex, thank you. All right, so yeah, I put this abstract in, and it was originally called Handling Complex Guest Exits with eBPF, which sounds really grand, and maybe that's why I got accepted. But in reality, I only did MMIO. So if you're interested in other types of complex guest exits, this isn't for you. Before I jump in, who am I? That's what I look like when I'm smiling. I'm an upstream kernel hacker. I'm 64 architecture co-maintainer with Catalin Marinus. That's the core architecture, not the KVM bits. I'm employed by Google in the Android systems team, mainly working on PKVM, which we spoke to you lot to death about at the last KVM forum. And I'd rather be fishing or brewing beer. So before I jump in, I feel like I need to give a disclaimer because I really don't know anything about eBPF. Does anyone here know about the internals of eBPF? Maybe Alex, someone at the back. Great, I might need your help afterwards. Okay. Yeah, I've definitely got, there's plenty, like, this was kind of an excuse to play with it, but I definitely have more questions when I started. It's a work in progress, it's all a moving target. I'm not even convinced it's a sensible idea, but I'm hoping to plant a few seeds. I do think it's cool. I did fix a code gem bug in the verifier, so at least something good came out of this work. And it was very much conference-driven development. When I put in the abstract, I had no code, didn't really know if this would work, and then it got accepted, so I was kind of, need to make something work. So I got a prototype, which I'm going to try and demo if I have enough time. So you should all be familiar probably with the basic model for I/O handling in KVM. This is an MMIO type thing, or VirtIO in this case. So I'll just whiz through this to sort of set the scene. So the application does some sort of write, goes into the guest kernel, chucks some data into the vring, which is a piece of shared memory for the VirtIO device. At some point, we're going to trap because we're going to ring a doorbell, and that's that write L at the bottom. That goes out, routed through the hypervisor, and on ARM64, we go back into the host kernel via this IO member abort path, which in the traditional model then goes back to the VMM and user space with this KVM exit MMIO reason. And then QEMU here can figure out what it wants to do with that. It can go and look at the queue, it can process those descriptors, and probably issue system calls back into the host kernel. So it's a bit silly because you kind of go out just to come back in again on the host side, which, you know, it's performance, it's latency. So for some devices, you can do better. You can keep that handling in the host kernel using this thing called vhost. So now you can see, I mean, QEMU still had to do some work here. It still knows about the device. It's had to do some IOC tools to set it up. But once it's up and running in the steady state, you kind of just stay in the host kernel handling those exits. And that's faster, and that's widely used, right? But it does have some limitations. It does result in thousands of lines of device-specific C code running in the host kernel with elevated privilege because it's in the host kernel. It doesn't really need the privilege. It's just we don't want to go out to come back in again. But it's not brilliant. It only supports VirtIO. If you want to use other device emulation in the kernel, then you have to use this KVM create device IOC tool, which I'll talk about later. But that's then all device-specific interfaces. The VMM still needs built-in knowledge of the device because it needs to be able to drive the vhost configuration, for example. And it's hard or impossible in some cases to update these at runtime. You need to reboot the whole host to update your device, which is obviously painful. You've got to migrate guests off. And like I said, it's privileged code running. It cannot be sandboxed. So after a few beers in the pub, I was like, you know what? Maybe this is a paraphrase of me, I think. Maybe we should use eBPF to handle guest exits. Oh, cheers. Yeah, right. Well, actually, I thought about it the next day, and maybe we could, right? Let's give it a go. I need something for KVM Forum, and it was only September. I haven't really done much since then, so let's put this in. So can eBPF save the day? So eBPF, for those who don't know, is a bytecode language originating from the networking side. I think it's Berkeley Packet Filter, and then they extended it. I think it's extended. Yes, extended Berkeley Packet Filter. So this is a bytecode where you can upload programs into the host kernel and attach them to certain parts of the kernel, and they can then run in response to different things like receiving a packet, for example. And it's quite cool because when you load those bytecode programs into the kernel, they go through a verifier, and this verifier will check, for example, that you're not going out of bounds of an array and trying to access kernel data structures. It'll also try to check that you have bounded loops, which probably isn't possible in a general case, but it will reject programs that it doesn't like the look of. It's quite flexible, so there's an API from user space, which is then portable, so in theory you can upload these programs regardless of the architecture, and the kernel will JIT them to the underlying machine code. And there's also an interface to the BPF programs themselves. So a BPF program can call certain functions within the kernel. So it kind of has its own sort of system call interface, but they're not system calls, they're just function calls. And they're called BPF helper functions that you can invoke. It's pretty fashionable, which is really good for conference submissions, as I am proving. On the downside, like what I'm trying to do is quite atypical. Handling guest exits for MMIO is not really the kind of thing. I think it's pushing at the edge of what you might want to do with eBPF. The permissions model in particular is very rigid. You know, you have these helper functions you can call, and if you have no privilege, you can call this bucket of helper functions. And if you have a bit more privilege, you can also call all of these other functions. And if you're root, you can call even more functions. But it feels a bit, you can't say, I just want this helper, or I want this helper but only with these FDs, or you don't have that kind of fine-grained thing that you have with system calls. And it's fashionable, which is also bad because it's moving really quickly. So what have I done? So I did some hacking, and I came up with this new kernel in-kernel device, which is KVM dev type BPF, and I'm going to just explain a bit about how that works. So I've modified the previous diagram. I haven't managed to get VirtIO working, so this is just a really boring MMIO access, but let's just say we've got an MMIO exit. We're going back into IOM abort down the bottom into the host kernel. What happens in this model is instead of dispatching to the vhost driver, we dispatch to a program in the eBPF JIT, which has been attached by QEMU. And effectively, that allows the BPF program to handle the MMIO exit. And so we should get all the benefits of vhost in terms of latency and performance, but hopefully none of the downsides, because you can upload this stuff at runtime, it's sandboxed, you can update it, the VMM might not need to know very much about what's going on, which is quite scary. So here's the programming interface from the VMM side. So the dev type BPF is a new device type, and you instantiate one of these in the prototype I have with this KVM create device ioctl, and then you can set attributes on that device. And the main one you can set is you can actually set an MMIO range where you want these programs to run. So that's the struct you pass from user space. The addr there is a guest physical address. So you can say, you know, a guest physical address blah, I want however many pages of MMIO space, and when the guest does an MMIO read on that region, I want you to run the program specified by readFD, and if it does a write, I want you to run the program specified by the writeFD. And those FDs are file handles that you get back from the BPF system call after you've successfully loaded your bytecode programs. So it's kind of two steps. You load your programs first, then you attach them to MMIO space. libbpf makes that really easy. It's just like as a function you call to go, hey, just go and load this for me. And if the verify is happy, you get your FDs. I think you can do a similar interface for virtual interrupts. I'm like halfway through implementing that, and I ran out of time. I had to do the slides. But I think you can attach virtual interrupts and then signal them as well from BPF. So that's the VMM view to BPF. The other side of the sort of interface is what the BPF program itself sees. So when you attach your read program, for example, and you get invoked in response to an MMIO read, you get a single pointer, which is a pointer to the context. So this is the structure I've come up with. This is quite interesting for a bunch of reasons. I'll just walk through the fields, and then I'll talk about why it's interesting. So we've got a 64-bit or 8-byte buffer. That's the transfer buffer. So either it's, you're either reading the data there or writing it, depending on the direction of the MMIO. You've got an offset within the region, which is the offset that is being accessed. So you might be like a certain device register, for example. The length of the access and padding, and then the vCPU ID. I'll talk about why we need that later. But the interesting thing about this struct is it's completely fake. It's never allocated. And this is kind of one of the flexibilities of BPF that is quite powerful, I think. When you access fields in this struct, the JIT will JIT accesses to actual internal kernel data structures. So if I read vCPU ID here, I'm going to JIT an access into the struct vCPU and pull out the ID, but without exposing struct vCPU in the kernel user API, which I think is quite cool. So this is like your interface to the underlying data. And it also means that you can do things like, for example, if you're in the MMIO write handler, I can make the buffer read only, and I can refuse to load a program that tries to write to the buffer. So you get sort of fine-grained permissions on what these programs can and can't do. So your program runs. If it returns 0, handled, skip the faulting instruction, back to the guest. If you return non-zero, we're going to go back to the VMM. Maybe we couldn't handle it for whatever reason. So that's cool. What? How do you sort of package this up? So I've tried to come up with this concept of having a device as an ELF file, which is quite interesting. It's not the normal way that you ship BPF programs or distribute BPF programs. And basically, I take you get an object file. I'll show you this in a minute with your read and write functions, and then I add this note that I've come up with. It's just some formatted note, an ELF note, which describes properties of the device. For example, how much MMIO space it needs, what its device tree compatible string is, or what its ACPI description is. And you can, in theory, then get to a point where the VMM doesn't need to know anything about the device. It can parse the note, figure out how to tell the guest about it, attach these programs, and you're away with a mixer. Linkers really hate this, so I had to use optcopy, but you'll see that. Linkers just segfault when I tried to link this thing. So this is what I just described. Probably should have skipped ahead to this. So you've got your functions on the left-hand side, along with a note. You compile that with LLVM. So you don't have to write this in bytecode. You can write it in C, or if you're cool, you can write it in Rust. You then partially link that to get your relocatable ELF file, which you can feed to the VMM. In this case, I'm using KVM tool. That will have instantiated this dev type BPF. We can attach the programs to it. And now when the VM takes an MMIO exit, it's handled in the sandbox, and it can call into these helpers. So that's kind of how it works. Shall we try and do a live demo? So this is probably not going to work, but let's see. Can everybody see that? Okay, thank you. So this is just on an ARM64 hacker, so this is an AR64 environment, but it's just running in QEMU TCG on my laptop, so it's really slow. It's really, really slow. So you can see this is my hacked up 6.3 kernel with all that stuff in that I was talking about. So what shall I show you first? If we go into this BPF devices directory, this is a standalone directory where I've got two devices. The one I'll talk about is the PLO31. That's an ARM real-time clock, right? It's a simple device, but that's the one I've just had a crack at emulating some of it. So let's just have a quick look at that. I'll show you roughly how this works. So, okay, boring stuff at the top. We've got some register definitions. You can just get that from the technical reference manual. And this is C code. Here's the structure I was on about earlier on. The fake structure, it's missing the vCPU ID because I don't need it here, but it doesn't matter because it's never allocated. So the first thing that's interesting is this maps section. So this map section is, this is what you use to have, basically have global state. So you create here a BPF map. So a map is, you can have things like hash tables with maps. You can have things like arrays per CPU data structures, whatever. I'm just using an array here, a 4-entry array of U32s. That acts as the persistent device state. So the read program and the write program can mutate the maps, and it will persist after the programs are finished. So that's what you can sort of use to just have the internal device state. And I've just got 4 because there's some 4 registers. Then I have these helpers for reading and writing those registers. So you can call, here's invoking a BPF helper, BPF map lookup LM, right? So that's how you index into the map. So that's for reading a register, that's for writing a register. I've got some funny stuff here for calculating some time. Look, some more BPF helpers here for getting the international atomic time, for example. Because it's RTC, I want to find out what the time is. Here is a read program. So this is all macro soup, but hopefully you can see we have a read program. It takes in the context pointer. We extract the offset. We switch on the offset. Then depending on which register you're accessing, I either just read it out of our shared state, or I calculate what the value should be based on the international time, or I just return some hard-coded values because there's some ID registers at the end. So it's very simple. You can see there I'm just setting the buffer to be whatever the ID byte should be. And at the end, we'll either return 0 because we liked it, or ENXIO if it was a register that we don't implement. And the write program is similar. So we can build this, ignore the opt copy invocation that's going to fly past eventually. Yeah, that's horrible, ignore that. Get rid of it. Right, now what I can show you, if we look in here. Okay, so we've got our ELF file, and you can see, hey, it's eBPF. We can look at the sections of this thing. You can see our note. Oh, I'll show you the source code for the note as well, because that's a little bit interesting. There's a whole bunch of different things. And here are our read and write programs. You have to put them in their own section because libbpf wants them like that. Yeah, sorry, I meant to show you the note. Let's have a look at the note. So the note is, I mean, this is just, if you've ever looked at creating ELF notes by hand, it's fairly painful. But for example, here I'm saying the compatible string of the device is ARM prime cell, so that the VMM can create a DT node from it. What else can we do with this? We can probably obj dump it if you want to have a look, in case you don't believe me. Device.o. Okay, this is what BPF disassembly looks like. So here's the read devreg function. It'd be nice if it was sort of formatted better, but you can see here's the call to that function that does the lookup, right? Oops, watch out for that. Okay, so I'm going to boot a guest first. So first of all, I'm just going to boot a normal KVM tool guest. Remember, this is in TCG, so it's pretty bad. And you can see this is without the RTC, so we're stuck in 1970, which is probably better for music, but not a lot else. So let's get out of 1970. And now what I can do is, if I pass, you can see now, sorry, can everyone see that? Is it too low down? I don't really know how to make it go higher up, but I'm passing minus BPF, and then I'm passing it the ELF file that I was obj dumping earlier on, right? So all I'm saying to KVM tool is use this. KVM tool has no knowledge about RTCs at all. It's just going to take in this device, it's going to parse that note, generate the correct DT entry, and then attach the programs. So now, hopefully, if we scroll up, you can see, I'll leave it at the top, you can see sort of here that it's found the PLO31, this is our emulation, and it's set the clock, and it's not 1970 anymore. So that's cool, it's working, right? Sorry, this is going to be at the bottom. I don't really have a way of fixing that. I guess I can hit enter a few times after each command. Control L. Yeah, didn't work. Okay, so there we go, put it up. So you can see I ran HW clock -i. You can interrogate the clock like that. What else is interesting? Yeah, I know what we can do. So if we switch back to the host, so this is a root shell on the host. BPF has lots of tools associated with it, so you can do things like BPF tool prog show on the host, and you can see our IO read and our IO write functions are loaded into the JIT, right? And there's lots of information about how big the program is, and BTF IDs, and when we loaded it, and what the UID is, and that kind of stuff. There's a map ID of 1. So we can dump the maps. So here is that PLO31 reg map. That's our array, right? You can see it's 4 entries. So that's what's keeping the state. And you can then do things like, the syntax for this tool is horrible. I will make a mistake at some point. So you can dump it, right? So this is quite cool. We're now introspecting the state of the device. Actually, all the guest kernel has done at the moment is enable it. So there's like a 1 in the control register. The rest of it hasn't been touched. And you can even do things like serialize it into JSON. So maybe you could migrate the device if you were feeling brave. I don't think you can import this, but there's no reason you couldn't have a way of importing the internal state, right? If you wanted to migrate a device emulation. What else? Oh yeah, so there's a thing you can do. You can actually manipulate the map as well. So if we dump it again, now the syntax for this is really complicated, so just give me a minute. I think it is. You have to pass a key, which is the index, but for some reason you have to pass this as a series of bytes in big endian. I don't know why. Probably because it's from the networking people and it's faster. Something like that. Okay, so I just updated the value of index 0 to be 1. So now if I go back to my guest, which is still running, okay, way, the music's good again. We're back in 1970. And then you can also set it again from here, I think. If we want to go home because we're sick of work and it's time to go to the pub, then you can set the clock to 5:30. and we should be back in the current time. Yeah, it's time to go to the pub. And if I dump the thing here, you can see now that lots of different register states been changed because there's 2 different registers that are programmed by the driver. So that's like the demo I have. Let's go back to the code, not the code, the slides. How long have I got? 10 minutes. All right, let's run through this. So one of the other motivations for this was some scheduler work from Sarah Vanner and David, who can't be here, but they're in my team at Google, and they helped me put this together, so I just wanted to give credit to them for that. So the problem, you'll see how this ties in a minute, just bear with me. There's a problem which Sarah Vanner has discussed, and there's stuff on the list, and it was discussed at Linux Plumbers. You can go and have a look at his slides. I just stole this from there. But what we see on Android is we get pretty bad performance when you have asymmetric big little systems, so CPUs in an SoC of different performance points and power points, and we have dynamic frequency scaling. And the guest doesn't know anything about this, so you get things like this, where you have a CPU-heavy workload, and on the host, if you run it, it starts off on CPU 0, so this purple box here is just the thread running, in case you're not familiar with these, and here's the frequency underneath. So you can see, hopefully I'm not too much in the way, but you start off on the small core, and it's CPU intensive workload, and the frequency gets ramped up. And at some point, you run out of frequency, right? You can't make that small core any faster, so the scheduler says, well, okay, well, we're gonna have to do it. So it shifts you over to the big core, and then you see the frequency ramping. And the whole thing, after 181 milliseconds, you're Fmax on the big CPU, right? Great, we kind of did a good job as the scheduler. But if you're in the same workload in a VM, we never get off the little core, just because the guest has no concept of that topology and no way of communicating to the host what it needs. So we get quite bad performance from that. Keep walking into this. So there's more information about it. You can have a look at the series on the list. The way that they proposed solving this, Sarah Vanner and David, was to add a new CPU frequency driver in the guest, which makes sense. The VMM pins the vCPUs, okay, let's just assume that happens. The guest CPU freak driver can then expose some of the host CPU properties, like this, what's it called, the capacity, the frequencies that are available, and then it can issue requests which correspond to uclamp utilization values. That's a way of communicating your utilization using shared set ATA, the system call. But how do you communicate that? Well, initially I think they wanted to use hypercalls. Hypercalls are quite inflexible. It's an ABI for the hypervisor. Didn't really want to do that. Could use an MMIO device. Well, if we go back all the way to the beginning of my talk, putting that MMIO device out in user space is going to give us some latency. And for this kind of workload, it's really critical that you minimize that latency. Not only because the guest is runnable, right? We want to get every cycle spent on this path is wasted, but it's a fast path. Like the scheduler accesses these registers all the time, I think on every context switch. And the state of the system can change during that processing. So to keep the information up to date is really crucial. So we could do it with eBPF. So I had a crack at that. I had to add some new helpers. In fact, I can show you the code. Like, basically, there's some getters to get information. These are just returning information that you can already get in sysfs. The last one sets the uclamp values, so that's a wrapper around shared set ATA. I didn't want to expose shared set ATA in its entirety because it's a bit of a multiplexing system call, and you can do things like change to a real-time policy, which feels like something you don't want a BPF program to be able to do. But I'll just show you the code, and I'll explain these very rough numbers. Where is it? Here it is. So it's really, really small, right? As well as the font. I know it's a bit of a small font, but the code is also small, I promise you. So there's a read function and a write function. You can basically get the current frequency, or you can set a frequency, and we do some maths, and then we call the uclamp, right? It's not complicated. Oh, is this going to take me back to the beginning? Please don't take me back to the beginning. Thank you. So some very rough results. I think these are literally from yesterday, so take them with a grain of salt. But running FIO under PKVM, so in PKVM we're bouncing IO. There's actually quite a lot of CPU involved. You can see, to get in user space, we get a performance uplift. So this is like 13% faster. That's 10% faster. And it's interesting, right? Because I'm not talking about like the cost of the accesses to the new thing I'm talking about, or the exits. I'm not talking about the actual IO throughput in the guest. But we were seeing sort of 23% for this one. This is the best number, so I picked it. But the random writes are 23% over this 13, or this is 15% over of that. So it looks pretty promising. These are pretty massive numbers. So I think that's cool. If you want to have a look at the code, I have plenty of hacks for you. I've got my host kernel changes, so that's all the stuff I spoke about earlier on with the new device type. I don't yet have virtual IQs working. I'm going to be getting that. I've got new program types. I'm maybe supposed to use this thing called BPF struct ops, which there's an LWN article about it, and it like makes your head spin. Yeah, that's all there. I've got this eBPF devices repository, again on kernel.org, which has the two devices I've spoken about, the PLO31 and the vCPU Freak, and the horrible build system to spit out those ELFs. The KVM tool, which I used for the demo, that's basically the code to drive libbpf. And then there's a guest kernel driver for the vCPU Freak device, which is in Gerrit here if you want to have a look. So it's all out there, it's all open source. And I think you can actually go slightly off piece with this, so it's already a bit wacky, but I've got some really weird ideas which are quite scary, and I just wanted to throw them out there in the last few minutes. So I'm quite nervous about the ABI and security implications of some of these. I don't quite know how to do asynchronous behavior. You can't block in BPF, so at the same time, it does have support for things like timers, so there must be a callback mechanism. I just need to spend some time understanding that. There's a scary helper called BPF copy from user, which would mean in theory that these BPF programs can go and slurp memory, if they've got enough privilege, they can slurp memory out of the vCPU thread that maybe corresponds to data structures that are, VMM data structures that are outside of guest address space. I think we should probably not want, I don't think we want that, but you could have a BPF guest access. For example, it could even take a guest physical address, and we could JIT the translation, or code to do the translation. And you could say this device can only access these certain parts of guest address space. I think that's quite powerful. Maybe someone could try and do vhost. I have no idea if that's plausible, but it'd be cool if you made it work. I think we do need finer grained permissions. Something like you have for seccomp for system calls. We probably need something for BPF helpers to be able to nail this down. PCR devices to get x86 working. Maybe using that JSON state for device migration. The crazy idea I had at the end, which might be going too far, is you could even have a device which just has like a firmware upload register, and then the guest could upload the ELF files for the devices itself. So then the VMM doesn't even need any device emulation, right? The guest provides the devices and the drivers. I think you have to fix the permissions problem before that is remotely feasible. But sounds pretty cool. And your idea here, right? So in the last minute, I think this is cool, but I'm really not precious about it. Like I said, this is conference-driven development. I'd love it if other folks could have a play, see where they can take it. We can turn it on its head, we can chuck it away. I just thought it was interesting to talk about, interesting to think about. It's surprisingly powerful, I think. The security story definitely needs figuring out for some of this. But yeah, if you're interested, the code's all there, get in touch with me. Have fun. Thank you. So there might be time for one question. I knew it would be Alex.
Of course it would be. Is it on? Hello, hello. Ooh, it works. So first off, disclaimer. I basically experimented with similar things without BPF, just basically as a prototype, just to see how it works. I don't know, like 10, 12 years ago, and gave a presentation on KVM Forum on that, if in case you want to see that. The main conclusion from that was, is as long as you live in an open source environment and ecosystem, and you kind of want to have things available and hackable for everybody, and you make the interfaces small and simple enough, there's very little reason to do any of this, even any device simulation in the kernel, because either you go and modify your guest host interfaces to be exitless, which is what you actually want, or you need to run legacy things. And at that point, you either do a device model in the kernel, which doesn't really help because it's half the cost.
So what would you propose instead for?
So for this particular use case you have, for example, for the scheduler, you would need to have, say, probably have something already in the kernel that polls for the current frequency, because your host needs to reschedule and analyze things, and you just basically move that into a shared page and share that page, and basically have
for the readers you could do that, but you still end up with device-specific code. That's the first thing. And the second thing, like for the set, I don't see, like setting a uclamp value, you could, when do you get that picked up? Like you need to, because you need to act on it quickly.
Sure, but I'm not convinced that the exit to user space is really a significant performance impact.
I mean, I had
for
numbers,
the
right?
rights.
Like, if we can have a look at the numbers.
For the rights, only
Okay.
for the ones where you say like I'm hitting a threshold, I really need to go and do something proactively here now. You can probably even be smarter on doing them.
I
even
mean,
less.
it is, right? Like,
This
you
is
can
all, this is
see-
including for reads. This includes reads. So if you make the reads exit free, and you make the writes be slightly smarter, you don't need to write on every single time, right? You can
Yep.
basically write only when you exceed certain thresholds to actually go and jump to a newer frequency or whatever
Yep.
you want to give as permission. I'm pretty sure you'll see very similar performance
Okay.
numbers, or even better, probably even better than the BPPF MIO one, because you're not exiting. So the main conclusion I had back then was, as soon as you exit, you lost.
Yeah, so if you,
Because
so when I
it's
talked about
synchronizing.
the helpers earlier on, right, you could, I said there's this like user access functions, right? So if we had guest memory access functions, you could do exactly what you're talking about. You could have a BPF device that has a shared page, and that's the only page it can access. And you could even do things in the verifier and say, for example, the device can never read the page, it can only write it, and it can only write
You're
these
still
fields.
exiting.
No,
But
no,
the
you
problem-
wouldn't necessarily be exiting for that.
You're exiting. Well, if you're exiting the guest to the host, right?
It depends when you decide to run the program, right? So if you get the asynchronous stuff working, you can have a callback, and you could say, you know, when the value changes in the host, then you
So what-
won't write it to
So
the
what
page.
I think would be super cool is if you could do something similar where say your firmware in the guest could inject a BPF program into Linux to basically do device emulation straight inside its own context, right? That would completely remove any exits. But as long as you still take the exit from EL1 into EL2 back into EL1, all that dance, you already spent most of your time context synchronizing.
All right, we're out of time. Thank you, Alex, for the question. And
So two things, one related to the talk and one related to KVM Forum. Related to the talk, last year at KVM Forum, someone proposed the app calls from the guest using eBPF, and people were a bit worried about the ABI stability,
Yep,
of course.
I can understand that.
So I'm not 100% sure, but I think it was also scheduler stuff. And the other thing is that after Alex's talk, we're going to go outside and take a picture.
okay.
Yes. Speakers. Awesome. Great. Then it works. Say again? Yeah. Thank you. No, I'm good. I want to stand here and talk to people. All right. 1 second. Much better. Hello and welcome to the continuation of fun things we're doing for conference-driven development. This is, I'm going to talk about how to run macOS on macOS for now, on Apple Silicon. So there's lots of apples inside apples. You need to do AI these days, right? Who am I? I'm Alex Graf. I'm a kernel hypervisor, whatever you want to call it, developer at EC2. And I basically built the cloud. That said, This is not related to the cloud. That was just a side project where I was like super excited to see how Apple did a few things and was like, oh, I want to see how that works. And the way I usually try to understand how things work is by rebuilding them in QEMU, at least when it comes to low-level tech. And that's how we ended up with this presentation. Small flashback. Last year, I gave a presentation on hypervisor framework, what it is, how it works. If you want to run QEMU on macOS with hardware acceleration, what you do is you basically run QEMU, which calls a special thing called hypervisor framework that gives you pretty low-level access to registers to run virtual machines, so that the macOS kernel can be fully locked down and you don't have to modify anything there and install your own hypervisor there. And then you can run a virtual machine with that. Now, what Apple also did in addition to hypervisor framework is they released something called virtualization framework. Great names, right? Virtualization framework is a library that calls a separate or creates a separate VMM process and has an RPC interface for you to communicate with that separate VMM process, which then goes and essentially takes over the role of QEMU, right? So virtualization framework is basically Apple's version of QEMU as a library. And that one creates virtual machines and you can go and run Linux. But this talk is not about Linux. Turns out, virtualization framework also recently, I think like 3 years ago, gained support to run macOS virtual machines on Apple Silicon. And that's what all of this is going to be about. So if you want to run virtualization framework, there's a couple of tools there. I usually use macOS VM because that's in Objective-C. I don't know Swift. Most of the other pieces are in other languages, or proprietary. Parallels, for example, uses this. I think VMware Fusion is also working on a backend for virtualization framework because that's the only endorsed way by Apple to run macOS VMs, and people kind of want to do that on their Macs. What happens if you want to use I'm going to use macOS VM as an example throughout the presentation on how to use this. You can use your others if you want. What happens if you try to create a virtual machine there is you first need to install it. So Apple doesn't ship installers anymore. What they ship are recovery images because everything these days is a phone. I'm not kidding you. Like literally, like you get this picture across the presentation. Everything is a phone. You basically get this recovery image that you would usually use to recover a phone, and you, instead of recovering the phone, you basically recover your virtual machine from there. So that's the installation flow. And what you get out of that is a root disk image, an aux image, a type of device description, and machine ID. And we're getting there on what those mean in a second. You can then take these and say, go, please, virtualization framework, go and run this now, and then you get a virtual machine. Easy, right? Well, let's look a bit deeper down underneath the hood. The disk image is just a raw disk image that contains the actual contents of the disk. However, its root volume is encrypted. So usually, like by default, you couldn't just go and map it and read it. The aux image contains in VRAM. I don't know if you've ever used Macs or macOS. If you did, something they basically carried over all the way from PowerPC into now is an NVRAM concept where you had first open firmware variables and then UEFI variables, and now it basically is parts of some NVRAM storage that is virtualized with the aux image. It also contains a copy of iBoot. iBoot is the bootloader they use on phones and on new Apple Silicon Macs as a bootstrapping entity. We get to that one in a second as well. The hardware model is super obvious. It basically is the same as the -m flag in QEMU. There's nothing there. It just says, please use this particular device emulation version so that you can run older versions of macOS on newer versions of virtualization framework. And the machine ID is literally a single variable, which is the ECID. We're getting into what the ECID is in a second. If you look at macOS, the underlying kernel is the XNU kernel. Well, we usually are used to having a single kernel for everything there is, but on and that is the case for x86. XNU. But on Apple Silicon, what they did is they basically changed that mentality from a single kernel away to multiple kernels depending on your generation. So you have the M1 kernel, the M2 kernels, the M1 Pro kernel, the M1 to M2 Pro kernels. And you see like there's something that looks different here, right? This one doesn't look like a bare metal kernel. Well, it turns out what they actually did is they introduced a completely new device model that is not the real machines at all for virtualization. And that one is part of the stock macOS images these days. So if you run macOS, you have a full environment on there that is able to run on virtual machines. It's always shipped. But what does this VM Apple thing look like? What is it? Well, turns out it actually is pretty standard. Like you have CPUs attached to this device model. You have a normal interrupt controller. It basically uses the Gig V3. You have, which is very different from real Apple Silicon, by the way. I don't know if you know the internals. You have normal RAM at a fixed offset, simple. You have a GPIO controller for the power button, the same way that we do it on the Virt machine model. You have a PL011 standard ARM serial device. You have a normal RTC, the one that Will just described, also lives right here. Also, newer versions now do a PV one. And you have actually the QEMU PV Panic device lives in that VM Apple device model. I'm pretty sure they prototyped this on a well-known hypervisor. And then you have a pretty stock PCI Express bus. Sorry if you cannot see this bottom down as well. But down here it just says PCIe. They have a pretty standard PCIe bus. The major thing that's slightly awkward is that they don't do interrupts whistling. But meh. The rest is standard. But there are some non-standard devices, things that are particular to the VM Apple device model. You have obviously, you have a very special case boot RAM that brings up this particular device. We get to that in a second. You have a special config region. You have the backdoor interface, is what I called it. I'm sure there's a different name for it, but the most obvious one to me is literally backdoor interface. You have a graphics, virtualized graphics entity, AES engines. It's a phone. And a special Apple VirtIO block implementation, which is, I'd say, 95% compatible with actual VirtIO block. So if you look at the booting story, how do I boot this device, which explains the first three devices we're looking at. When your CPU comes up, it runs the boot ROM, like everything else, right? Well, the boot ROM turns out to be called AVP booter. I don't know what that stands for. Apple Virtual Platform, no idea. And it lives in this path on any macOS installation that you have. It's a special build of iBoot, so the same standard bootloader they use everywhere. And the only purpose it has is to access the config space for some configuration purposes, and then that backdoor interface to basically read out stage 1 from the aux volume. Once you read out stage 1 from the aux volume, it shows you a nice dump on the serial port. That one comes up and reads stage 2 from the root volume. So now you load stage 2 from the root volume, which comes up, shows you a nice splash screen on the serial port, and accesses the root volume again to go and read out the actual kernel to boot the XNU kernel and it jumps. That's blazingly fast, like all of this happens in, I don't know, a couple of milliseconds, right? But you'd always have this boot chain going from boot ROM to the aux volume, which would be your flash, your non-volatile storage, non-volatile flash storage on real systems, to something that is on the NVMe disk on real systems to the XNU kernel. So they basically modeled the exact same flow you would have on real hardware, on phones, on Apple Silicon Macs, also identically in the virtual machine, which is good. It means less divergence. But what is this config thing, right? Like what is in there? Well, it turns out it's really just a shared memory region. It's like a 16 kilobyte region of memory that is directly mapped into the guest. It contains things like how many CPUs do I have, how much RAM do I have, am I running in emergency boot mode to recover, or am I running in my normal boot mode? What is the serial number of my device? What is the CPU name of my system? So it contains a couple of things, and ECID, that's the important one. So ECID is very particular when it comes to Apple. It's the exclusive chip identification number. So that one exists in every single Apple SoC that you will find, and they're all unique. So this is how Apple ties the flash of your system to a particular phone, so that when you take off the flash, you can't just go and read out data from someone else. That's how they protect your data on your phones. And because of that, it basically by default always is used as the encryption key for your root volume, which makes it super annoying. It essentially means you cannot take a root volume from one device and put it on from one virtual machine and attach it to another virtual machine, because as soon as the ECID is mismatching, you're toast. There's like, you just cannot access any of that data. So you always have to carry the ECID around as well. So we cover those. Let's look at para-virtualized graphics. One thing Apple did with Apple Silicon, which is a break from any previous generations of macOS that I'm aware of, is they make 3D rendering mandatory. So in older versions, in PowerPC, there was no 3D rendering until later on x86, they had 3D rendering as a software rendering fallback backend. So you could basically bring up everything in 2D only, and then it would do things like LVM pipe internally to do 3D rendering. For Apple Silicon, they basically decided to get rid of all of that and only do real 3D rendering. And the way they do real 3D rendering is by something called para-virtualized graphics.framework, which is another library you can call that then establishes that device interface. And that's what, for example, VMware uses when you do macOS on x86 on macOS. Then they also get 3D graphics through exactly this interface. That one is that simple from a usage point of view, slightly annoying from a not running on macOS point of view. What you do is you're basically forwarding any AOMIO request to this virtual device, to the library. The library then has a callback to say, hey, I kind of want to have access to this guest memory. And then they just establish some communication channel, a ring buffer, something, and keep going. And you're completely out of the picture as the VMM. You just don't know. What you get out of that is a metal shader that you can basically render onto a screen and then show the contents of that graphics device. So if anybody is interested in reverse engineering, cool toggle, really, you should look at it. AES engines. So every phone has an AES, or every modern phone at least has a modern Apple phone has an AES engine. It's the device that's virtualized in VM Apple is exactly the same device as in every iPhone and iPad and whatever you have out there. It basically is used on boot and for other things to hash data, to either create hashes for signatures or to validate signatures of things. It contains embedded keys. You can also configure your own keys. I don't remember if it actually uses that feature. But it mostly uses the embedded keys. I do hope these keys are slightly more random on real hardware. They're not very random on VM Apple, but I'm very fortunate. Like I'm very happy for them to keep it simple, because otherwise it would have been much more pain to actually reverse engineer all of this. So if you cannot read in the back, the keys for slot 1 is 1, the key for slot 2 is 2, and the key for slot 3 is 3. Those are 6-bit values. Cool. So that leaves only the VirtIO block device, which is particular. The Apple VirtIO block device is pretty much a standard VirtIO block on a different PCI device identifier, so that it doesn't collide with a normal VirtIO block number space. And it has a hard-coded Apple device type identifier at a fixed offset of the config space, which means since they didn't update the spec to have that included, they now collide with the zone extensions, and now we have 2 different values at the same location. You can only use one over the other. They also introduced a new block command, which I inferred as this is basically a trim with 0. So you have a clearly defined command that just says wipe this data. The patches are on the list if you want to review today, tomorrow, over the weekend. By all means, have a look. That's super simple. You see it's like 12 patches, I think. It's not a lot. It's also not a lot of code. So enabling all of this virtual machine framework, virtualization framework, VM Apple backed device model is like less than 3,000 lines of code. It's not. It's simple. It really is simple. Okay. Paulo just said the backdoor interface smells like a 15-year-old KVM code. I'm not sure. It may. It may. I don't know who actually was the mind behind building this device model, so there could be overlap. I don't know. So how do you use all of this? Well, if you have these generated images from virtualization framework where you went through the installation step, we don't do installations on QEMU now. If you have these files, then you take them and you pass them into QEMU. You need to pass them twice because we need to pass them once into the backdoor interface and once into the actual virtual block interface. Backdoor interface for iBoot, actual virtual block interface for XNU and beyond. So you take your root device and pass that in. You cut off the first 16K of that aux image and then pass it in as a device. Then we ignore the hardware model, that's basically just -m. And then we extract the machine ID from that encapsulated, mangled, whatever thing. So it's a plist, it's an ECID value in a plist in a base64 encoded variable of a JSON inside a JSON, I think. Either way, you run the script and you can just get the ECID. And then pass that in as a UUID parameter to the machine model. Eventually, the command line looks kind of like this, right? You pass in the VM Apple as BIOS, you pass in an actual UUID, you pass in the P flashes, you pass in the drives, you say use HVF. There's no way right now to use this with anything but HVF, and off you go. Which means we can now take a look and see if the demo gods are pleasant. There we go. So here, can you read this? Probably not, right? I don't know how much you have to read because most of this is going to be graphical, but I will build a small run script to do all of the cutting and whatever myself and extracting of the parts. The way it's easier. But you see iBoot coming up, right? So we have iBoot. So over here is the AVP booter printing some debug info. Then you have iBoot stage 1, print some debug info, iBoot stage 2, print some debug info. And down here, the XNU kernel is starting, and did not configure this VM to emit serial output from XNU. Otherwise, you would also see that there. And then you have a normal macOS virtual machine running that is slightly unhappy about the screen size. And you can use it like you usually do with any of the virtual machines you have. You can browse the internet if that loads. If you actually connect it to Wi-Fi. Am I connected to Wi-Fi? Oh, I see. That's why. Oh. So it just uses VirIONet with a normal backend. This is just using Slurp for me on the host, but I'm not online. It did work in the in the hotel room. So what issues do we still have outstanding? I hammered it a couple of times. I never really managed to get a keyboard working properly. If you pass in a USB device with a USB keyboard instead, you get like hanging keys sometimes. Something is off with the interrupt somewhere, I think. VirIO keyboard doesn't work. The VirIO tablet thing works just fine. I don't know. It's something to debug eventually. There's no access to the total store ordering feature of macOS. So macOS can switch individual processes and even virtual machines to enable total store ordering for x86 emulation. And that's a private entitlement, which you cannot do as a public open source project, so you don't get access to do your own total store ordering. So we don't get Rosetta. It's running on macOS only right now because of two reasons. One is it really requires an Apple Silicon device with HVF. HVF handles a few things in kernel space that are particular to this platform. And it also requires per-virtualized graphics framework, which you don't have anywhere else, unless somebody in this room or somewhere else on the stream or wherever would be interested in figuring out how exactly it works, and instead pipe it into, I don't know, like a Vulkan API. Would be great. It also currently uses the proprietary AVP booter, which is kind of bad. Like, you don't want to use a proprietary initial early first boot firmware. We do have C BIOS, we do have open BIOS for exactly those reasons. It should be trivial to rewrite and do that, just do our own copy. Cool, with that, questions?
So would the total store ordering be possible if you disable system protection or SIP?
Wait, the speaker is right behind me, so I don't actually hear. Say again?
So you're saying the total store ordering is not possible without permission from Apple, but would if you disable SIP, would it then be possible, or?
Okay, I grasp Rosetta, Apple, something, and disable. Oh, I see. If you disable SIP, if you disable SIP on macOS, you can give yourself that entitlement, because then they no longer check for every single permission check for entitlements. They remove a few. Worst case, you just disable Amphi, and then you can do some changes to QEMU to basically, when the sysregs to enable Rosetta get called, you just ignore them and always enable TSO for the VM. So it would be possible with if you disable security, yes.
Yes, I have two questions. First question, can you run iOS, like phone images in this VM as well, or only macOS?
I think the honest answer is I don't know whether the phone images actually contain VM kernels today. If you would ask me for my hunch, looking at the market share and sizes of what Apple's revenue is, I would be very surprised if they didn't use this technology to eventually build virtualization for older versions of iOS.
And the other question would be, in your change list for your patches, I saw there were changes to RISC-V vector, RISC-V interrupt controller. I was wondering.
I think there was just a file path something, or an API change. That's just a generic tree-wide thing. There's nothing particular about RISC-V at all.
Okay, yeah.
It's
Thanks.
just like you had to touch some file just to plump through some information somewhere.
Okay, thanks.
Okay, thank you.
All right, thanks.
So yeah, I hear this working. So welcome everyone to our talk on Verde OFS. I'm Hannah, that's Herman. And first, we're going to talk about Verde OFS in the present, basically. Current projects that we're working on, which include live migration and the integration with other projects. And then before giving an outlook on future plans, Herman will also give an introduction to Verde OFS from a technical perspective, basically, which will be interesting to you if you're looking to implement your own backends for Verde OFS, which are not Verde OFSD. So maybe you don't want to just share normal directory on the host, and then you write your own backends, and then this will be interesting to you. So Verde OFS allows you to share a directory that's on the host with the guest, simple as that. To do that, we have the daemon Verde OFSD, which has access to the shared directory and then exposes it to the guest through a Verde OFS device using the Verde OFS protocol and the Fuse protocol wrapped into each other. And then in the VM guest, you have a client who accesses this device and thus gets access to the shared directory, and that's it. So when you run Verde OFSD, there are a couple of options you should be aware about. I think most of the options are fairly well explained in the README, but there are some options that you should really set probably because they're important and Verde OFSD cannot figure out a good default generally for you. So one of these, for example, is caching. Caching is always a trade-off between safety and performance. And so, well, Verde OFSD doesn't know what safety you need. Of course, you always need the best performance, but safety is up to you, basically. So you need to tell it basically what caching guarantees you want. Like you can set disable caching altogether, simple as that. And then, well, every call from the guest, everything that you do in the shared directory has to go through the whole device, through the whole stack, so that's rather slow. But you'll see every update on the host immediately, so everything's very safe. Alternatively, you can set the caching to auto, which I also think is the default. In this case, metadata and the guest will be cached for a second. So you'll see updates rather quickly, but not immediately. And you'll have a default, and you have read cache for files. So if you're modifying files concurrently on the host and the guest, this might already cause problems then. With cache equals always, this cache is also kept when you close a file on the guest. So you can't just then close a file and reopen it to see changes on the host. That won't work then anymore. And basically every metadata, all metadata is kept indefinitely. So yeah. And finally, if you basically only if you have complete exclusive access to the shared directory by a virtual machine, you can also enable write-back caching, which gives you even more performance. But if you don't have exclusive access to a file and someone else modifies it concurrently, like that's really bad, because then the cache gets out of sync, the VM flushes it back, and then you might get data corruption. So really only use this when you are sure you can. Another option that we have is inode file handlers, which requires a bit of context, but this will also be important later on. So how we address inodes in the shared directory is through these Fuse inode IDs. So every inode gets an integer ID when the guest first sees it, looks it up basically. And when you want to do operations on it, you need the integer ID as the primary identifier. It's an ID. And so Verde OFSD must generate these IDs when the guest walks through the shared directory. And then it must also be able to open these inodes again when you just pass the integer ID to it. So we need to keep some mapping of these integer IDs to inodes. And the question is, how do we represent these inodes? How can we open them just from the ID? And there are two ways we have. First one is the file descriptors. So when the guest walks through the shared directory, we open the file descriptor, and we just keep it. And then later on, we can work on this, operate off of this file descriptor. And that's very simple. The problem is it's a file descriptor. So first, it counts against Verde OFSD's file descriptor limit. So there's a count limit that you have. And if you hit that, well, the shared directory is too big. So that's too bad then. The second problem is that it keeps files open. So if they're unlinked, for example, well, the data will not be deleted immediately, right? How it is with file descriptors. And this might cause special problems with NFS, like NFS v3, where you have silly renaming. So when you delete a file, NFS cannot really delete the inode. So we'll rename the file to be a hidden file, and that's maybe not great for you. So in these cases, alternatively, you might want to use file handles instead to represent inodes. How these work is basically they're just pure data that point into the inode table of a file system, and then you can hand this data to the file system, and it will later open the inode for you immediately. So the advantage is it's just data, so it doesn't count against all these caps. It doesn't keep the file open, but the disadvantage is that it requires basically root privileges because it requires this very heavy-handed capability, CapTech research, and also file system support. But the file system support basically is a given because most file systems support this. But the root requirement, of course, is something that you generally cannot assume there is. So you need to set this based on your use case. Like if the file descriptor limitations are a problem for you, then well, you want to use file handlers probably, and then you must ensure somehow that Verda obviously also runs this root. If you can ensure that, well, you should switch off file handlers. You can also just let Verda obviously figure out whether file handlers work or not, but better set it explicitly. Okay, now let's talk about something more interesting, live migration, because that's always interesting. So the question is, why is live migration a problem for Verda OVSD? The problem is that we have internal state. I just talked about this mapping of inode IDs to inodes, and we also, of course, have file descriptors for every file that the guest is open, and we want to do IO through it. And the thing is, we need to transfer state to the destination and restore it there. So we have two problems there. First of all, we need to turn this state into data. And second, we need to move the data to the destination. So we need a serialization problem and we have a transfer problem. The second one is simpler, so let's talk about this first. We can just get the data to QEMU. So QEMU already has a migration channel. We have a connection to QEMU, so let's just give it the data. QEMU puts it in the migration channel, and we're done, basically. There's several advantages. First of all, we don't need any additional configuration in Verda OVSD, so we don't need to point it to the destination explicitly, because it has the connection to QEMU. Second, no additional privileges required to open a network connection, because we already have the connection to QEMU, again. And then QEMU has some nice features for the migration channel, like migration to file, for example, and we all get these for free if we just let it handle this transfer. This will require an extension to the VOS user protocol, of course, to transfer the data across, but I mean, nothing that's unsolvable. The serialization is a bit harder and comes with its pitfalls, basically. So the question first is, we have these two internal parts of our state. The first one is the mapping of inode IDs to inodes. We've already seen that inodes can be represented through file handlers. They're already data, so we can just put them into the migration stream as they are. The problem is, first of all, again, requires root privileges on the destination to use the file handlers. And second, file handlers are only valid on the very same file system that you generated them on for the very same directory that you generated them on. So you can only migrate Verda OVSD if you are using the exact same directory between source and host. So for example, with shared storage such as NFS. If these requirements cannot be met for your case, then we probably have to use file paths instead. The idea here is basically we walk through the whole shared directory, we look at all inodes, and we compare them to our internal database, and we thus find some path to the inodes we have. For every inode we have, we find some path that works, and then transfer this to the destination, and then we use the path to open the inode again. This would allow you to migrate between different file systems, different shared directories, just need to be copies, basically. Doesn't require root privileges, but, well, if you're migrating between different directories, then you have other problems like external renames, for example, where basically it's a time of check to time of use problem, right? You generate the file path, and then the file on the destination is renamed, and then the destination can't find the file. So that's too bad. So basically, both of these approaches come with their pitfalls, so we'll need to implement them both eventually. We're currently focusing on the second one, but we will implement both. And then it's up to you, the user, to figure out which one of these best fits your use case, and then you'll have to choose. Basically, the question is, do you have a single shared directory between source and destination? Probably should use file handles. Otherwise, probably should use file paths. Now we have the other part of our internal state, which is open files. And that's even funnier because, well, they are file descriptors, so we really need to get these across to the destination. But you can't. Like, you can't get a file descriptor across a network connection. So the idea is to take the inode ID and the open-add flags used for it, and, well, reopen that on the destination and repeat the open process. But that's, of course, a problem if the file's been deleted in the meantime, or if its permissions have been changed, because then the destination will not be able to repeat your open process. And the question is how to solve this. The answer, we're not sure yet. like this is definitely something that will be not solved in the first iteration that we release of live migration. So these will be limitations at first, and then later we'll have to get creative. Maybe take a leaf out of NSF's book, try something with silly renaming, I don't know. But we'll try creative solutions, definitely. But a completely different approach can be taken if you have a very special case where you just basically, for example, want to upgrade QEMU. So you have one host, want to migrate from one VM to another, but you don't care about VirtualFSD at all. Like, it can stay where it is, it can stay the same, you don't need to transfer any data there. In this case, you can just keep the data there and basically disconnect it from the source, reconnect it to the destination, and be done. All the FDs are safe in there, so none of these crazy problems will happen to you. And in this case, you might want to have a look at the external migration work from Anton Kucin, which would allow this. And with that, I hand over to Hermann.
So, who is using this? Basically. Currently, it is also kind of a critical part of Kata containers, VirtualFSD, and also is used by Core OS assembler to build the images. But I want to highlight a couple of use cases that we had that I find interesting. One is Dracut. Now is VirtualFS is included in Dracut, so you can in the command line kernel you can say, okay, I want to run this virtual machine from this directory. So the QEMU only needs to access the kernel init.rd, and you instead of using an image like QCOI2 or something, you can directly boot in from a directory that is sharing using VirtualFSD, for example. I think it's kind of similar to what Kata does. And now it's also integrated in systemd, the ftab generator. You can do the same, but not only for the root file system, but also for any other mount points, like, for example, home. And that is, I think, is interesting. Especially from the Dracut part, if you need to develop like a kernel code. Now also KDump supports VirtualFSD, so you can generate dumps directly in the VirtualFSD directory, so that's nice. Very convenient. Also KubeVirt. Now you can share config maps, secrets, network APIs, and service accounts, persistent volumes using VirtualFSD, and that is nice, especially in the first cases. They share config map, secrets, and the rest of resources, because the previous method was using ISIO image, like a CD-ROM disk image. So they were copying all the data in that image and that exposing that to the VM. And if that information changed, that, for example, the secrets of the server's accounts also can expire by time, etc., you will not see that propagation of the change inside of the virtual machine. But with VirtualFSD, we solved that problem. And also we can use the previous one, the support in Dracut, to use to say to KubeVirt to boot from a persistent volume, for example. So that's nice. This is one way, for example, to the thing that we add is the file system device, that you need to define which one is your volume, and that will be automatically exposed to the VM. How VirtualFSD works? Well, VirtualFS is a fuse file system. I will try to explain very briefly how that works. So first, I want to explain a little bit how fuse normally works. So when you have a user space application that does some file system operation, will be first handled by the POSIX file system layer in the kernel, and then it will call the fuse client in the same kernel. And the fuse client will send some fuse operation using the fuse protocol to the fuse daemon in the user space via that fuse character device. So basically, that is the normal flow of the communication between your application and the fuse daemon in the user space. And the thing is, everything is in the same machine. Let's say both the user space size and the kernel size is in the same machine. In case of VirtualFSD, since it's a fuse file system, we have the same basic building blocks. But in this case, the virtualFSD, the Fuse server is in the user space, but in different machine, in the host, and the kernel side is in the kernel, in the guest inside of the virtual machine. So we need to communicate those. We cannot use the same device, so instead we use a VirtualIO device that usually has two parts, the driver and the device. But actually, virtualFSD is a vHost user device. So that split the device in two parts also, the front end and the back end, and we communicate those using a Unix socket. For that Unix socket, we only use the vHost user protocol. And using that vHost user protocol, basically one of the most important things that we do is to set up a shared memory region with the virtqueues. We will use that virtqueues to send the Fuse command from the kernel guest to the Fuse server in the user space in the host. So the whole picture is something like that. So now the application, when it does some file system operation, it will be handled by the POSIX file system in the kernel. That will call the Fuse client in the guest kernel, and will send an operation to the Fuse server in the host user space via the VirtualIO device and the virtqueue. So easy peasy, basically. So, okay, that is more or less a very brief description of each part, how it's fitting in this scenario. Future plans. Well, first, live migration support now is our top priority, at least the basic support that was Hannah was talking about. We also want to make easier for people to use virtualFSD not only to, for example, implement other types of file system, not only pass-through. We have some people that want to use like a native NFS client, for example, or CephFS. But also if you want to include your virtualFS inside of your VMM. Like, for example, we have a project now that they're including the virtualFSD functionality inside of Cloud Hypervisor, for example. So that is one of the things that we want to make easier. It's possible now, but it's kind of not easy. Also, we are working to remove all the sandboxing code for the virtualFSD and use an external tool that will make much easier to be included in a container and all other stuff, because usually virtualFSD is already run inside of an external sandbox. So that is to simplify also the use case. Also, more in the future, we have this VirtualIO vHost user support. That is the idea to have, instead of having the virtualFSD in the host user space, that will be in another virtual machine, in the user space of a different virtual machine. So the communication will be between virtual machine and virtual machine. So you can share a resource from one virtual machine to another. That use case, for example, was asked for people that has drivers from some file system inside of the virtual machine, but not in the host, and they want to access those using virtualFSD. Also, we are working on read-only sharing, IO urine support, to coalescing operation to make it faster. And also, we think it will be nice to have the iNotify stuff that probably allows us to implement more features in the future. So basically, that's it. 1 minute before the mark. So thank you.
So more of a comment than a question. So the feature you were talking about of trying to make it a crate is something that is also used by the Rust version of the runtime for CADA. And one of the reasons for doing that is essentially to bring in process, in a single process, things that were running in multiple processes before. One of the issues when running virtualFS as a separate process is that you can have, for instance, a low memory condition where virtualFSD crashes, but QEMU is still there, or the opposite. And then these are situations that lead to really confusing error messages, and it's hard to recover from that. So there is also sort of simplicity for the user value to being able to have that in process.
Yeah, that's a basic idea, basically. You can do that now, but it requires more work that is really needed.
How complex that would be to migrate the inode information, and does this make sense to migrate the WhatIO based FS? So instead for use cases, maybe a block thing, WhatIO PMM or something else could be used just and input. Yeah.
So I didn't get the question fully. Like for live migration?
Yeah, you mentioned about WhatIO FS live migration future work. So
Yeah.
first question is how hard it would be to implement that or get it correct?
I mean, we're fully correct. And we're currently working on implementing it. So we already have a working prototype, basically. But it's well, the biggest problem basically is its work across all layers. Like we have Rust grades that do the VOS user stuff. Then we have to extend the VOS user protocol in QEMU. So it's just taking time. I don't think it's very hard to get something done. It's taking time. And then we have all these problems about correctness.
And for the use cases mentioned, does this make sense to use a block-based?
To use what?
Block-based solution like WhatIO PMM or something for use cases?
We haven't looked into this yet, but so.
Okay.
Just want to say, I think in some cases people actually want to share the directory and not necessarily like block devices. I think this Kubernetes case, they want to share some secrets with the VM, but they also want to basically do something like refresh the secrets. So having a block device makes it really harder. Sharing a directory makes it really easier. So there are some use cases where you need a file system-based interface and not necessarily block-based interface. So it helps with those use cases.
Okay. Yeah.
Thank you, manager.
So for the case where you want to migrate a file that has been removed, I think you mentioned the ability to delay the link from, so what you would say is something like, I know that this file handle is in use, and I just keep the file around so that I can reopen it on the other side. But the obvious question then is, what is the name of the file on the other side?
I mean, also the question is like, what is if someone else deletes it outside of WhatIO FSD? Like.
So you can't completely hide it. You could hide it on the source, but on the destination, it's harder.
Yeah, as I said, we haven't really looked into this yet. Just brainstorming, just oh, these are problems, and yeah. So we're happy for input on this, right? But
yeah, or
maybe you can drop another file, some link to it, so that like original file will be gone, but my temporary file will be around, so I can still find out the destination. I know, crazy idea, but dropping more files in a big file system will be a problem. Yeah, so like maybe something like NFS silly rename files, like
yeah, probably we need to do something similar.
Or prefix it with something, and if FSD is specific, and just hide all the files when the lookup comes. So, but none of these are elegant solutions. I'm just throwing them out there, and like, if you ask me to implement it, I probably wouldn't do that.
Basically, we now want to, since this is like a big problem with a lot of corner cases and weird interaction and stuff, we wanted to be concentrated only in the simplest case. That is, we have lots of assumptions. For example, is both in the target and in the source in the target, we have the same files, and those didn't disappear and didn't change the name or anything. So it's kind of, especially for the QBIRD use case with service accounts and secrets, that is what we can expect. So it will work if you do some modifications, mostly, but we are attempting to solve this for like a read-only case. And we expect that nothing changed from the moment that you shared that directory to the migration. That is the first thing that we want to solve. The rest is just speculation, what we do. But yeah, we have a very, very clear case for that is NFS, that there is for them, except for NFS version 4, that is not implemented in the server part. I tried it unsuccessfully, is the silly rename stuff. So yeah. Also, it's not only that, it's if we want to support the temporal files in the open, that you don't even have a name when you create that file. So that's another case that we should support in the future.
Great, thank you.
Thank you.
Okay. Hello, everyone. My name is Emanuele Giuseppe Esposito. I work at Red Hat. Today I'm presenting with Kevin Wolf, also at Red Hat, and he's also the maintainer of block layer. And we are going to talk about the multi-queue in the block layer. So how we are making the block layer thread safe. So what are the challenges that we are facing? What are the problem, the solution, and so forth. So first of all, let's start with a small introduction and what is our goal. So many of you already know the block layer is basically something that sits between the guest block devices and the host storage, and it's capable of read, write data from and to host storage, interpret image formats, manipulate the data on the way. So when I try to learn to understand how it works, I basically see that is internally is some sort of graph. It gets pretty complicated graph, but where each node can be a device, but also can be a job, or and there are also intermediate nodes that are used internally. And this graph is a runtime is also modified, and it's read and written by multiple threads too. So there is already the need of a synchronization, and it's already implemented in some way with the IO context lock that we will see afterwards. Yes, so from the device, from the guest perspective, the view is it's pretty nice. So we can see that requests coming to a device, they are split in multiple virtual queues. So this is pretty nice from the guest perspective. But when we see the internals right now in QEMU, is that there is only one IO thread. This is basically processing all the virt queues. So it's like a bit weird. So, and our goal is essentially this, so to allow multiple IO threads to access the virt queues. More specifically, one IO thread can access multiple virt queues, but one virt queue is only processed by a single IO thread, a specific IO thread. So this sounds simple, but in reality, we had some challenges. So the first one is called the IO context lock. So as I said, there is already some sort of synchronization in the block layer. The history is that at the beginning, we only had the main loop and the BQM lock. Then it was IO threads were introduced to improve performance, and they access the block graph. That's why we need this IO context with per IO thread with a lock. And at first, it was only protecting the block driver state, so it was nice. But today, it's basically used everywhere. And by itself, today, QEMU works, of course, with each image or device is bound to a single IO thread. But when we want to improve performance to add multiple IO threads, as I showed before, this won't work anymore. Yeah, as I said, the IO context is everywhere. So we went to look VirtIO block SCSI, you can see the IO context lock, block backend, same IO context lock, and the list can continue. And this is not good at all for us. So the first step was to understand what is running in the main loop and what is running in an IO thread. So the first step, the first thing I did was to go to the headers, for example, block.h, and divide all the function in categories to understand what is, and I added also a lot of macros, really a lot, to all the function to assert and be sure that, for example, the global state code function, they represent only the function that run in the main loop, so they will fail, the assertion will fail if they run somewhere else. And there are also rules. So the category has global state code, IO code. So IO code is only running in the IO thread, so it should be thread safe. IO or GS code is like can run without the BQM lock, but only in a specific IO thread. And then there is the common function. And they have rules between each other. For example, global state code function, so the running main loop can only call other global state function. The second step was simple, replace the IO context lock with another lock. So in some places were pretty okay to replace the context lock. For example, in the job API, we introduced the job mutex. There is also thread pool, and there are other minor APIs. Virteo, Block, and SCSI, it wasn't so easy, and I think Stefan and Kevin are still working on it. But I will classify this as a kind of easy step. The hard step is to replace the lock for the graph modification. So as I said, the context lock is everywhere, but there are some, for example, callbacks that are recursive, read the graph. Of course, if we modify the graph while something else is reading it, will end up bad. The good news is that there's only few places where we actually modify the graph, and mostly they are just readers. And now we talk about the possible solution that we have. The first option was drain. So there is subtree, drain, begin, and end. We called it politely ask the others to leave the graph alone because it's some sort of cooperative way. The nice thing about this is it's already present in the block layer code. And basically after, the way it works after drain begin, basically there is no more IO processing that is coming to submit to the block layer, and the running ones, we wait till they are done before returning from the function. So it could be used as some sort of lock for what we needed. The disadvantages is that, yeah, it's by itself already recursive because it has to scan the whole graph to stop the IO or finish it, make sure that it finished. The purpose for the drain was not this, and there are not the right guarantees according to Kevin. Something else can still send a IO request. Yeah, so there are some disadvantages. And the conclusion is that Kevin removed the subtree drain the API from the QM block layer directly altogether because it wasn't a good fit, and also it was also not used correctly already. The second option is simply a read-write lock. So because, as I said, we have many readers but few writers, and basically reader should be a coroutine that basically blocks when a write is happening, and writer first waits that the reader are done, and then doesn't allow new to enter. And the advantage of this is that the locks are explicit and mandatory, so it do not require cooperation, unlike the drain where if there was basically no enforcing. And another nice thing is that the lock are added in the block API, not everywhere in the whole devices and jobs and whatever. So just local to the block API. The only disadvantage is that, of course, there is already the IO context lock, so it has to live together with the IO context lock, at least for now. So it's a little bit difficult to make everything works. And also, these callbacks, as I said, the readers should be coroutines, and not every callback in the block driver state are coroutines, so it's a little bit difficult. We need to convert a lot of functions. And now I will hand it to Kevin. They will talk how we make sure when using the read-write lock that it's correct.
Yeah, so as Emanuele already mentioned, we choose the read-write lock. It's actually a very simple lock. It's just one global lock covering everything. So in a sense, it's not what you would initially have expected, because you would expect if you replace the AO context lock that is already quite coarse-grained, you would go to something finer-grained. And this is actually more coarse-grained because it's not per thread, but it's global. But also, as Emmanuel already said, we have very few writers. That's essentially an explicit user action through the QMP monitor. So it doesn't really matter. And one global lock for everything is really enough. So the question is just now how we do implement this. And so there are a few simple rules, really, or that look simple. Basically, whenever you read the graph, you need to take the read lock. That's obvious. For example, IO request that you have that goes to some image, for the whole path that it takes to the block graph, you need to take the lock, because otherwise the block graph could change under your feet while you're doing IO, would mess everything up. So obviously, you just take the read lock. If you want to change the graph, you take the write lock. In the implementation details, the challenge is that not all of QEMU's code is asynchronous. So we can reasonably assume that most of the code that will read the graph already runs in the coroutine. Coroutines are nice because they are asynchronous. If you need to wait for a writer who already has the lock, you can just yield to the main loop and wait until the write lock becomes available. There are some more readers. If they run in the main loop, basically what is the global state code macro that Emmanuel also mentioned before, then it's fine to access the code, because the only writers that are allowed run in the main loop as well. If you're reading in the main loop, we won't get a concurrent writer. Right, so this is a rule. If you want to read, you need to be in a coroutine. If you want to write, you need to be outside of a coroutine and running in the main loop. You also, and that is a rule that we kind of detected only a bit later when it was already implemented and things were breaking. You also must make sure that you don't hold any AO context locks while you want to take the write lock, because what it does is it waits for readers to complete by running a nested event loop. And when you run a nested event loop, and you actually, what was I going to say? I mean, running event loops could run essentially any callbacks that happen, and those could again take a lock. And because the writer didn't actually just yield in the background, but it's running a nested event loop, then you get deadlocks. So that's not something that works. So we need to be careful there. And also nested event loops, if you hold the AO context lock of a different thread and you're waiting for that thread to make progress, that's not going to work because you just locked it. Right, that covers the next thing as well. Okay, and then we get to the problem. It's a reasonably small set of rules, but actually enforcing that, like looking at the code and finding out, do we actually fulfill all of these conditions? It's not that easy. So that was already the reason why we didn't go with the drain, or one of the major reasons, because it was just too hard to make sure that all of the users of the block layer correctly respond to a drain request. But it's still kind of hard with a read-write lock with ditch, which is a more standard approach. So what we looked into is, let's actually get help from the compiler. CLang has this warning called TSA, Thread Safety Analysis. And with that, you can actually just annotate your code. You can say this function needs the lock, or this function can't be called while you hold the lock, stuff like this. Then you turn on a warning flag, which in QEMU we do by default if it's available. So if you compile QEMU on CLang, you will get that warning flag enabled. And then if you do something wrong, like you're calling a function that requires a lock, but you don't hold it, then the compiler will already refuse to build your code. this TSA has some, it was originally built for C++. It works also with C, but it has some major limitations. So these limitations, one of them is really relevant for the block layer, which is that it doesn't cover function pointers. So if you're calling a function pointer, then it doesn't check that you actually have the logs that this function needs that is called by the function pointer. We try to get relatively close to the same semantics by marking the file, the function pointer itself as requiring the log. So while you read the file system pointer, you need a log, but for actually calling it, you don't. So if you copy it out and then call a function, you're not covered, but you're still covered if you directly call, like, I don't know, the B drive read callback of block driver. You can't have a mutex inside of a struct itself to protect fields in a struct, which is not a problem for us because we just have this one global block graph log. If you want to use it for something else in QEMU, that could be a limitation. The third one is TSA doesn't understand essentially the cleanup attributes, which are used in the mutex guard macros. So if you use those, the results are not as reliable. So it, for the graph logging, it's preferable to actually use separate lock and unlock calls instead of using the scoped guard macros, which is actually not that bad because the reason to use the scope guard macros is essentially that you remember to unlock, right? Whenever you exit the scope, then you release the lock again. And TSA actually already makes this sure. If you forget to unlock a lock that you took in a function, then the compiler will complain. So this is what it actually looks like in QEMU. We have macros for the block layer, graph WRlog and graph RDlog. You just add it to the function, and that's it. And it tells the compiler that you need to hold the lock if you want to call this function. As I said, function pointers, we annotate differently so that you have to take the lock to read the pointer. There's a separate macro for that. And if you're outside of the block layer, which probably many of you are, but you're interested in using the same kind of threat safety analysis, I suppose that could be interesting for other subsystems as well. You can directly use the macros from the header file, because the macros that we use in the block layer are really just simple macros that expand to those TSA underscore whatever requires guarded by, which in turn are also only small wrappers around attributes that actually tell the compiler what to do. So users outside of the block layer can use these directly. And then apart from TSA, there's also a tool called VRC that was written by Paulo. It essentially allows you to analyze the call graph in QEMU. So you can basically you match functions and you can see path between these functions. Functions can be matched by name, you can match them by regex, so you catch multiple functions, or you can assign labels to functions. So you group functions into functions with the same label. These labels could either be present in the source code itself. It's again a compiler attribute. And we actually do that for the coroutine related markers like coroutine FN. So those are automatically available as a group that tells every function that runs in the coroutine, or that must run in the coroutine. Or you can also have a text file where you explicitly define this function is in this label. And with this tool, we can find path and, for example, find functions that are non-coroutine functions and call coroutine functions directly without, just spawning a new coroutine to run it, which is a bug. You can't do that. Or you can find places where functions that run in a coroutine run nested event loops, which is not allowed either. So these are some kinds of bugs that we stumbled upon while making the conversions. And this tool is a help to find them. Right, after we know how we can ensure a bit more how to keep things safe, let's go into the plan of actually implementing it. So the plan is relatively simple. So we just look at each function that touches the graph, essentially the links between nodes. So anything that goes to a child node or that goes to a parent node from a given block driver state from a node. If we want to access that link, we just need to take the log. So first step is you just take it locally around that access, and then you start pushing it up into the callers. If it's a coroutine caller, that's easy because you just can take the log. If all of the callers run in the main thread, that's the exception that I mentioned before, then we're actually safe. We can pretend to take the log because we know any writers would run in the main loop as well. So we don't have anything we need to protect against because we're in the main loop. And then there are the cases where the code is currently not running in a coroutine, but it needs to take the log. In that case, we need to move the code to run in a coroutine. And the usual way we do this is using the coroutine wrapper macros. And there's a script that then generates wrappers that spawn the function in a coroutine and wait until the coroutine has finished and return the result. So we're already using, or we have already been using these functions for block I/O, like read functions, write functions. They have already been doing this. And we essentially need to extend the same mechanism to more functions. We actually did this, so this is pretty much finished. Right, and once we have covered all of the places that access the block graph, then we can actually add the TSA annotation that tells if you want to access the children or the parents field, then you need to have the log. Once this is done, you can get rid of the AO context log for protecting the graph against changes. So we did this and moved functions to coroutines, and it turned out that it's not so simple because we actually overlooked some problems or some things that we need to consider. The coroutine wrappers, as I said, they spawn a coroutine and then they have a nested event loop to wait until the coroutine finishes and returns the result. These nested event loops using AO wait while, they have the property that they drop the AO context log of the thing that you're waiting for, because if it runs in a different IO thread, that IO thread needs to make progress so that the coroutine can actually finish and you get a result. Now, some places never even took the log. So trying to unlock a log that isn't even locked, get an immediate crash. Somehow these callers got away with it before. Probably in a usual case, you just didn't get any concurrent accesses, but it was wrong. And so with this change, we saw it because we saw QEMU crashing. So we just needed to actually add like the necessary locking to the places that should already have had it before, but didn't. Also, we need to be more careful about only calling coroutine FNs from coroutines and no coroutine FNs not in coroutines. Especially the latter case was something that the code didn't always adhere to. So we were calling functions that should never run in coroutines, but we were calling them from coroutines, and with the changes, it actually caused deadlocks. So these are actually not hard to fix, but they're just many places to consider. We went through them. Should be done by now, hopefully. Then the other thing is AO context locking. As I said, the rule is while you're trying to take the right lock for the graph, you can't hold any AO contexts to avoid deadlocks. And in many cases, it wasn't even clear in block layer functions which AO context lock they're holding, or the caller is expected to hold. So this needed some cleanup as well, so that we can make sure to actually unlock it before we run nested event loops. So while the goal is eventually removing the AO context lock so that we can actually submit from multiple threads, we actually need to fix it first so that we can even make the steps towards this. So block drivers are already ready for multi-queue. Letting TSA check that the links are protected. This is in progress. I've already got quite a few patches merged. I have some more locally that I still need to send out. I have something compiling that already asserts that the parents and child links are only accessed while you hold the graph. So the compiler accepts it. I'm still cheating in some corners by essentially telling the compiler to trust me. That it needs a little work still, but NAND is inside. Then we need to check that the remaining fields of the block driver struct are correctly locked as well if you access them. And then finally we can start submitting requests for multiple threads. Right, and finally, some numbers, some benchmarks. So before we even started to make all of these big changes, we tried to simulate the multi-threaded environment before we had it. And Stefan did that by basically not submitting requests from multiple threads to a single image, but we're just opening the image multiple times and then assigning each to one thread, because that works even before that. And that's kind of the theoretical thing where we should end up with the multi-queue code. So this is just visualizing the difference between the simulation and what we actually want to. So we can see that the virtual queue IO threads, these are the difference essentially compared to the single queue or single thread virtqueue model that we have today. Results are looking quite nice. With the actual multi-queue thing, Stefan also has a prototype for that. We're still missing something, so we're not getting quite to these numbers yet. But this is where we should get to with some more work. And that's it. So we're open for any questions.
Yeah, first thing when you said that changes or writers are mostly user actions, that comes to mind is RCU possible? But I think the data structure is not suitable for that, right? The graph?
It would be probably very complicated, yeah. So we didn't investigate it closer. It was mentioned, so we had a brief thought about it. But actually this read-write log is very simple, and the way it is implemented is it's actually just we have thread local counters for the readers, and only when you want to write, you actually sum them up. So it's relatively fast. You don't get contention there.
Okay, thank you.
Just thank you to Paolo and Stefan for helping us in the project.
Hello. So hello, my name is Eugenio Perez. I work for Red Hat as a senior software engineer, and I've been working in the Shadow Virtue solution for a couple of years.
Hi everyone, my name is Gautam Davar. I'm working as a senior manager software development for AMD, previously Xilinx. I have a huge team of 2 people, including me, who developed the VDP and net driver. So we are close to upstreaming it, so should be there in a while. But if you find any bugs, you can totally hold me responsible for them. So yeah, we'll go ahead then. So this talk is about VDP and net live migration with Shadow WordQ. I'll cover the basic concepts first, and then we define the problem that we see with SRIOV VF pass-through when we are trying live migration, and how VDPA comes as a solution to that problem. We then demonstrate live migration demo across 2 different hosts which have hardware NICs from different vendors. And then we dive deep into Shadow WordQ operation. I understand most of you already know about SRIOV, but single root IO virtualization is actually a concept that allows a single PCI device to be shared across multiple VMs as they see them as different physical devices. As you can notice here, you require a vendor-specific driver within the guest OS for it to be operational. So as the specification calls out, there is a physical function which represents the physical device, and there are multiple virtual functions noted here as VFs, which are passed directly into the virtual machine, and the data path bypasses the host kernel. So VM migration typically is very common. And what we understand from it is that we can migrate a virtual machine running on a host to a different host over a network. So basically the live migration aspect of it is that the applications and the guest operating system are actually running when that migration happens. Migration is totally useful for load balancing and managing with the hardware and software maintenance activities. And on the concept side, so as the applications run within the VM, they keep modifying the RAM, the physical memory, and they mark the RAM pages as dirty. So in order to make it continue operation on the destination host, we need to actually transfer those dirty pages until a threshold is reached. So it continues on the source host. Then we eventually stop the guest, transfer remaining pages onto the destination, and then resume operation or the execution on destination. So the problem that I mentioned a little earlier with SRIOV VF pass-through is that you need a vendor-specific driver. So here we are showing two different NICs on the source and destination hosts. So the source has got a vendor 1 NIC, so you need a vendor 1 driver for it. And on the destination, there is a other vendor NIC that is there. So when we attempt this migration, we need to stop the VM. We migrate this virtual machine to the destination. And then when we resume operation, it doesn't work. The reason is simple, that you need to load vendor 2 driver within the guest in order for it to allow data path. And that's the problem that we see with live migration of VMs using SRIOV VF pass-through. So before I dive deep into VDPA, a little introduction on VirtIO. So VirtIO is a specification that defines virtual devices, virtual drivers, and how they interact. The specification also defines how the data plane and control plane is created between the guest and the host. So data plane is nothing but the bulk data transfer that happens between the guest and host and the outside world. And in order to establish this data plane, we need control plane. And control plane basically defines a few concepts like feature negotiation, configuration of the V-rings, etc. To make it easy to understand, we have described the V-ring as just a circular ring of buffers, but if you see the data structures, there are a lot more fields to it. So this is just a very simple representation of that. VirtIO data path acceleration, more commonly known as VDPA. So how does it help, right? So data path is actually going between the guest and the device, as was in the case of SRIOV VF pass-through. So it bypasses the host kernel and the performance that we require is achieved. However, we have a generic VirtIO driver. So for other devices like block, this could be a VirtIO block driver. Here we are showcasing a VirtIO net driver. So the control path is actually intercepted by the VDPA kernel framework along with the vendor specific driver. So the vendor specific driver that was earlier within the guest is now actually moving to the hypervisor and on the host machine. So how this helps is that you have a direct data path, but the vendors can easily implement their own control path. Let's talk a little more about the data plane and control plane. So the red line again shows the pass-through data path from the VM to the device. Here I'll take an example to show how this translation of the VirtIO specific commands happen to the device specific commands. So here you can see there are some V-rings shown here. So typically in a VirtIO net device, there are pairs of word queues for data path. There could be up to N depending on the hardware. And then there is a single control word queue for passing on the control information or configuration information like MAC address, VLAN ID, the number of queue pairs that you want to configure. So this is an example where we are passing a command, VirtIO net control MAC address set command, corresponding to a command run within the VM. For example, if config ith hardware ether and then the MAC address to configure the MAC address. So VirtIO net supports this command. It will be intercepted by the vendor specific VDPA driver, and then it will be translated to the hardware specific command which needs to be which is required to configure the MAC address. For a Xilinx SN1000 device, this is called MC command set MAC. Now we see how actually this VDPA comes into play and how it resolves the problem that we earlier noticed with SRIOV. So again, we have a generic VirtIO net driver, and I think this was the cause of concern when we tried live migration with SRIOV. So here we have a VirtIO net driver. We have a vendor 1 NIC on the source host, vendor 2 NIC on the destination host. We have their corresponding drivers in the hypervisor, not the virtual machines. So when we migrate, we have to actually again stop the virtual machine at the source host. We transfer it to the destination. And then when we resume operation, this vendor 2 VDPA driver allows us to easily communicate with the VirtIO net driver, and hence the issues with SRIOV VF pass-through are not seen. So everything works well as expected. So we will be going to demonstrate this cross-vendor live migration. So this is the setup that we want to just talk about a bit. So we have two physical NICs on the source host. Both the machines are the same Dell 750 machines. The source is labeled as 28, the destination is labeled as 23. We have the Xilinx NIC on the source host, so we produce a VDPA device out of it, the VF, and the SFC VDPA driver allows communication with the VirtIO net driver. And next, on the destination, we have a Mellanox NIC, so we transfer the VM and see it will actually maintain data path connection during migration and after migration. So the other NIC on this source host is actually a secondary NIC just to establish data path. So this could be any NIC. So what we are trying to do, we are trying to run iPerf from the virtual machine, and then it goes via this Xilinx NIC to the switch, and it enters the data enters into this secondary NIC. When the VM migrates on the destination, the data path would remain the same. VirtIO net driver would send packets through the Mellanox NICs to the switch and then to the secondary NIC. So this is how this demo is to be established. In order to allow data path across all three NIC ports, we maintain the same VLAN ID on the switch ports, and we are using the AMD Xilinx SN1000 card on the source and Mellanox Connect X6 card on the destination. So over to Eugenio for the demonstration.
Okay, so here we have 4 panes. The top left one is the source of the migration, and the bottoms one are also in the source of the migration. We can see in the source that we have as a VDPA device in the port V3 that corresponds to the Xilinx virtual function. And then in the destination, we have another VDPA dev in the port 17 that corresponds to a Mellanox virtual function. We will run from the host to the destination. Here, I will send the migration command to the source QEMU, and here we have the iPerf server. So I start the source. You can see it's a pretty long command line for QEMU, but it is needed to set the minimum common set of features between the source and the device. You can see that even more parameters like VQ size is set at the minimum between the two, that is 256. And these kind of things happens like transparently. You also need to do this like for all emulated devices. So now the virtual machine starts, it's a Fedora. And now I start the destination QEMU. The command line is exactly the same except for the incoming parameter here that tells QEMU not to start the virtual machine, but wait for another QEMU instance to send it the virtual machine. So iPerf start. And you can see that we got a traffic of 45 gigabits per second. This is not really optimized. This is only to show that the live migration is possible and it works, okay? It doesn't have anything like CPU pinning or anything like that. And it's even using an, let's say, or not totally efficient virtqueue format that is called the split virtqueue. After that, we send the migration command here, and the device is suspended, and we switch to a mode that allows us to track the memory that the device is writing into. So the source QEMU knows that it needs to send those pages, those memory again to the destination because they are updated, and the destination guest should see a coherent view. After a while, the virtual machine is migrated, and we have all the performance again. So, okay. So we are going to do a little bit deep dive on how all of this works. As Gautam said before, the control virtue is bypassing QEMU. It reaches directly to the host kernel space. This is a problem because we need to migrate the device state that is composed by, as Gautam said, the MAC address, virtqueues, VLAN configuration, etc. And QEMU needs to track this device in order to be sent. So this is a problem. For example, if the guest tries to change the MAC address, the guest is updated, the device is updated, but QEMU is not aware of this change. So it will send a bad configuration to the destination, and the guest will see this change in the configuration suddenly. So the solution, as many other problems, is to add a new layer of indirection. From now on, the guest will talk with QEMU instead of the device, and QEMU will be able to track all of that. This is only for the control VQ, not the data path. The data path gets all the performance, everything the data path is passed through. But for the control VQ, QEMU will be able to inspect these kind of changes. So if we do again a MAC change address, it's propagated to QEMU, and then the device reads the QEMU V-ring. This is the actual shadow VQ, okay, not the guest one. When the device says it's okay, we can change the MAC address, everything is correctly updated. So good, so far so good. Next step is to actually transfer this state. There is no code change needed for this because emulated devices already needs to transfer all of these states. So all of that is totally reused. So the source have a few state noted, and then it sends to the device. Now, how to set all of this state to the destination device? Well, the destination device already knows how to handle all of these control VQ commands. So the trick is easy. We just enable the control VQ. We don't enable the data path. So the device will not try to write, for example, in invalid queues, or it will filter out valid packets. So after that, only the control VQ commands are sent. Again, the device and the driver already needs to know how to handle these commands. There is no change. Totally transparent for the device, totally transparent for the guest. After all configuration is updated, we can enable the data VQ, and the guest can continue happily after that. There is still one problem left, and this how to track this device memory modification. Since it's passed through, we have no way to tell QEMU that it needs to resend that piece of memory. Well, the solution is actually, again, to reuse the shadow VQ here. So to track, the shadow VQ already reuse all the emulated device code. So the track multi-memory is already in it. It was already there before implementing shadow VQ, so it's for free in terms of code. And every optimization that we do, either way, will benefit both. So how does it work? We need to actually stop the device and tell the device to start reading in this new shadow VQ, not to break the pass-through. But we need to do it in a way transparent for the guest, because if not, it will not be total live migration. So how is it done? We first allocate this shadow VQ V-ring. After that, we suspend the device and we fetch the VQ state, for example, the indices, etc. So we know how to present the shadow VQ to the guest. Okay. After that, we totally reset the device and we configure these new V-ring addresses in this memory. The guest doesn't have any kind of access to these new V-rings. After that, the device continues as usual. The device, again, this is transparent for the device. The device doesn't know if it's writing to the shadow V-ring, to the guest V-ring. There is no change needed in the device. So for example, when the device writes a packet, it will write to the shadow V-ring. When the device is writing to the shadow V-ring, QEMU is the one that will forward the descriptor. It doesn't copy the buffer, okay? The buffer is copied directly to the guest, only the descriptor, so it's kind of zero copy in that regard. When QEMU updates the descriptor, it is able to track the memory in the structure it uses regularly, that is the dirty bitmap. So a little bit of recap. I would like to do this. There is no change required for the device in order to track neither the device state, the dirty memory, or to restore the device state in the destination. In the future, it might be possible to opt in or opt out into any of these three items. Okay, so for example, if a device implements its own way to report the dirty memory to QEMU, we can use that. That it could be more performance, but still reusing the other two. Okay, so this is very flexible for vendors. And the changes to the QEMU code is actually really low. The only thing that it's not already there for each feature, for each new VirtIO feature, is to send the command through QEMU, through control VQ actually. All of them should be roughly the same. So here you can see a few vendors that already supports VDPA. Futures video demo could include like a bigger setup, but we didn't have such big setup with all of these vendors connected between them. But yeah, for future demos, it could be like really great to have all of these and start setting on and off different features, things like that. So after that, Batan will explain more about the Xilinx device.
So these are some details of the Xilinx SN1000 card that we used in the demo. So this is the same card that we developed our VirtIO or VDPA solutions on. So we have a full-featured VirtIO and VDPA net drivers working on this. We also did a VDPA block proof of concept. We do not have that driver in a state where it can be upstream. So it's basically one of the industry's first, or maybe the industry's first smartening offering, which actually allows software-defined hardware acceleration in a wide range of areas, for example, networking, security, and storage. So typical applications in these areas include Open vSwitch. In security, you can have IPsec, KTLS, or in the storage as VirtIO block, as I mentioned. So the major advantage or the highlight of this product is that it includes this FPGA device where the end customers can deploy their own application logic and use that using this P4 programming language so that they can actually tweak the existing custom offloads, or they can add their own new offloads. So in essence, you do not need to change the hardware. It is really flexible. You can add more features just by programming using P4. So this slide captures some of the blogs that are available on the Red Hat website in no particular order, but yes, one can easily go through them to understand more about VDPA. And I think these have been developed over the last couple of years, so very good information over there. And that's all. Thanks everyone for attending this, and time for questions.
Hi, so if we are thinking about safety I/O, then I'm guessing Shadow VirtQ kind of has no chance to work, right? Because the device here thinks that it's accessing guest memory, it's gonna encrypt everything, and then the host cannot understand what's going on, right?
You mean like the encrypted memory, like the confidential computing?
Yeah, there's extensions where you bring the device into the trusted
environment. So
the
I'm
trusted
not
element.
sure if about that. To me, you are exposing like this memory to the device through the IMMU. So I'm not sure if you can like configure the IMMU to trust in that area the same way as you will trust in a guest. I don't have that knowledge. Maybe.
Oh, these are the extensions that we had presentation about yesterday.
I will have to look into that and
So
there is another question at the back.
We can do this one. There is one question on the stream, and the question is: does the vendor-specific VDPA driver in the hypervisor using VirtQs as well?
Using what?
VirtQs.
Yeah, for the data path. Let me go back to this slide.
So actually the word queues are implemented within the device. So the device must be capable of VertIO data path. So vendor specific VDPA driver typically implements a set of config operations. So you can see them in a header file called vdpa.h. So the driver needs to implement all of them. So for example, it will implement a config operation like set varying address, wherein for a split word queue, you are passed 3 different addresses and you need to configure that on the device so that it is able to write into the guest memory directly. So there are no per se word queues within the vendor specific driver. I hope that was the question.
Are there devices already that don't need the shadow VirtQ and can do live migration on their own? And do you have some kind of performance ideas on how will it look like compared?
Still not, yeah. Still doesn't have any kind of figures about that because this, as I said before, this is still, there are a lot of optimizations like low hand free that we can get here. And all of that will require the vendor to actually implement a lot more. So this VDPA framework allows them to only implement that part of VirtIO, only the data path. So this is kind of the main target of this. If the vendor is able to implement all of the spec that the VirtIO requires for migrating, etc. But now it still doesn't have like those numbers.
Specifically for Xilinx, do you plan to implement it in the device?
I think not in the immediate future, but yeah, possibly sometime later. So yeah, I think the whole idea is actually software assisted live migration. There are solutions in hardware which we did not use for this presentation.
Thanks.
I mean, we can like opt in or on and opt out to these 3 different areas, and maybe we can divide in more areas. So maybe one of them, it is worth definitely like to track dirty memory. Maybe others are easier for vendors to implement in emulated or in software assisted way. We can work on that.
Okay, if that's it, then thank you.
Okay, thank you.
Thank you very much.
it work? Test. Okay, it works. Okay, welcome everyone. I'm Alessandro Di Federico, and Anton today, he's here with me. He's the main author of this work. Thanks for coming. So first, a couple of words on who we are. We are from Revenge Labs, a company that I co-founded, and we are building a decompiler that is based on QEMU and LLVM. As you might understand, those are two technologies we like a lot. But on the side, we're also doing consultancy on compilers, emulator, and dynamic binary translation. So today we're here to talk about a bit emulation. There are mainly two ways in which you can emulate, or let's say an ISA, a CPU. You can either write an interpreter where you have a C function for each instruction of the ISA, or you can write basically a small JIT compiler that translates instructions for the guest into instruction to the host, maybe using an IR, an intermediate representation that enables you to decouple things a bit. Turns out that in QEMU, if you want, you can do both. For what concerns the interpreter approach, you can basically write helper functions that are just C functions that are invoked at runtime by QEMU, or you can use TCG, which is QEMU's basically JIT engine. The topic of this talk is basically to automatically be able to go from the first option to the second one using LLVM. Specifically, I mean that if you have a helper function such as this one, which is a simple, let's say, a simple C function that takes two vectors in input and an output vector and just sums all of the elements in the vector, in this case 128, which basically you can imagine implements a vector add instruction, turn it automatically into a piece of C code that you can embed in QEMU that will emit a tiny code instruction, which is basically the intermediate representation that QEMU uses for its JIT engine, and just emit a symbol gvec add, which will perform the addition, and then the JIT compiler will emit the corresponding code. So brief outline, basically we'll do some background, and we will present the two approaches we've got for this effort. The first one is IDEF parser, and the second one, the one using LLVM, is helper to TCG, and then demo benchmarks and summary. So our original goal, since we're working with Qualcomm, was to write a fast open source emulator from the Hexagon DSP. The Hexagon DSP is a WLIW CPU, so you can run basically instruction packets. Each instruction, there are like more than 2,000 possible instructions just for user mode. And if you want to impress your friends, you can show them this packet, which is basically implementing a single packet, the inner loop of the fast Fourier transform. We already spoke about this a couple of years ago. So we refer to that talk if you're interested in how to handle a WLIW architecture and all the specifics of Hexagon. But yeah, let's focus on the predicated add instruction that we have, that we have in Hexagon. If we want to write it as a helper, we will have something like this. We have basically an argument for the predicate, and two arguments for the operands of the predicated add. And basically, at the beginning, we check the predicate, selecting the least significant bit. And if it's turned on, we perform the addition. Otherwise, we do nothing, and then we return the result. In tiny code, we will have something like this. We will have an AND instruction that takes the predicate, it ends it with 1, save it into a local variable, and then performs a branch conditional, checking whether lock is equal to 0, and then jumps to label L1 that we will bind later, and basically skip the addition. So if the condition does not hold, we just add R1 and R2 and save the result into R3. Or if you want to be a bit smarter, you can use a conditional move, because tiny code, the IR of QEMU, also have a conditional move. So you can perform basically the addition unconditionally, so you always perform it, but then you decide to write into R3 the result only if the condition that you want to verify holds. But you don't actually write tiny code directly. You have to write basically a piece of QEMU, which is called tiny code generator, and basically emit this instruction. So very briefly, you can see that here we're creating a new variable. We are emitting an AND instruction, creating another variable, emitting the add instruction, and here we are emitting the move conditional. So this is what we want to emit. So, but in practice, what is the difference between these two approaches? In order to understand it, we can look at the instruction the CPU, the host CPU, so let's assume that you're running QEMU on x86-64, is actually running. So let's consider again the predicated add instruction. This is how we encode it in Hexagon. If P0 R3 equals add R1 R3. And this is what you get if you use the helper approach. As you can see, there are some loads from at offset from RBP, which contains a pointer to the CPU state. Here we are loading R1, R2, and we are loading P0. And then we perform a call. We perform a call to the helper function that we defined before. And this function here has been compiled at build time by GCC. And GCC, by the way, was smart enough to use a conditional move. But this function is not, let's say, handled by the JIT at runtime. It's just a function that we compile at build time. So we compute the function, and then we store the result basically back into the CPU state. If we do it the TCG way instead, it's basically the same thing, but there's less, moving things around register to pass things to the helper function. We load stuff from the CPU state, perform again the conditional move and the addition and everything, and store back things to the CPU state. But now, in order to really appreciate what is the difference, maybe it's interesting to make an hypothesis and say, okay, let's suppose that all the operands of this predicated add are actually known at translation time. So right before that instruction, you have, let's say fixed values for those. In the helper option, you get exactly the same code. But if you use TCG, well, TCG has a mid-end optimizer that is smart enough to constant propagate everything, and you end up with just two instructions that just update the CPU state with the right values. This would just to give you a taste of why is it beneficial to go the TCG way. So to recap, helper functions, very easy to implement. If you know C and you know the semantics of the instruction of an ISA, you can implement it. But it's kind of slow because you have the hover for the calls, and basically you cannot perform any optimization at translation time. On the other hand, if you go the TCG route, it's fast, but it's also kind of tedious. You have to understand TCG, and it has its quirks, and I would say it's kind of a barrier to entry to support new architectures. So it has its own limitations. So why don't we generate this stuff? Why don't we go directly from a helper function to generating the piece of front end, the piece of TCG that we need? So our first attempt at this was IDEF parser. So this is specific to Hexagon. And here on the left, you can see what basically the good Qualcomm guys give us, what we call the source of truth, which is a pseudo-C language that basically describes the semantic of an instruction. As you can see here, we have the description of the predicated add instruction. We have some input registers, the predicate register, this is the output register, and the two operands register, or the operands of the add. And we just have if the lowest bit of the predicate is turned on, then perform the addition, otherwise cancel, ignore cancel. It's a quirk of basically the Hexagon thing. And that's it. So our idea is, why don't we write a small compiler that goes from this source of truth directly to the TCG? And that's what IDEF parser does. IDEF parser is a built-time tool that takes this input and outputs something like this. So you take the header of the source of truth and emit the header of the C function, part of TCG, and then here really quickly, when you look at the condition, we emit the code to basically emit an extract, which is similar to an AND. Then we handle the if statement itself by emitting a label, generating a conditional branch, and then we emit the body of the then branch of the if statement by emitting an add, a move, and so on. And then, yeah, we handle the else, emitting some labels and some branches. So this is what IDEF parser used to do. Now, this was written in Flex and Bison. It's currently upstream and maintained, and it brings some good results. It supports more than 1,300 instructions for Hexagon, but it has some downsides. Specifically, this is really tightly coupled to the source of truth that comes from Qualcomm. So it's basically can only be used with Hexagon. And also there's no AST, there's no IR. This is basically a syntax-driven compiler, very straightforward Flex and Bison syntax-driven compiler. But most importantly, basically we had to implement a poor man's C compiler, which is something I do not suggest people to attempt. So we thought, why write a poor man's C parser when we can use a real compiler, right? And after all, tiny code is an IR, and compilers, C compilers often use an IR. So why not translate IR to IR? And this is what helpers to TCG is about.
So exactly as Alessandro said, instead of going from pseudo C code through IDEF parser and ending up with TCG code, why don't we start with C code, feed it through Clang to end up with LLVM IR, the IR of Clang and LVM, and then feed it through our helper to TCG tool to translate it directly to TCG code. This brings us 4 main benefits. Firstly, again, we don't have to write a poor man's C front end. And then it turns out that translating an IR to an IR is much simpler than like a pseudo C language to an IR. And by relying on LLVM, we're also able to use a lot of built-in optimizations that exist already, and we're able to write our own optimizations on the IR. And finally, this allows us to create a tool that is completely architecture independent and can be used outside of Hexagon. So I want to spend a little bit of time introducing you to LLVM IR in case you haven't seen it before. We have our predicated add example here on the left again. And now I'm going to go through like a mapping between C code and LLVM IR. So we can see that the header of the function is pretty much, it's very similar. We have our integer types as i32s, and we have our registers as arguments again. The first thing we encounter is an instruction which is not present on the left-hand side. This is an alloca instruction which creates a local stack variable which we need to store the result. We'll see it in a little bit. But then we continue on and we compute the AND with 1 to get the least significant bit again. We perform an icomp instruction which compares against 0, and then we branch on this result to either the if label here or the exit label. In the if branch, we perform the addition and we store the result. And in the exit label, we simply load the local stack variable and we return it. Now, say we want to just manually translate this to Tinecode to see what it would look like. We start out with the alloca and store. We can simply map this to a move to a local variable. Then the AND instruction can be mapped to an AND in Tinecode. The icomp can be mapped to a set condition. The conditional branch in LVM can be mapped to a conditional branch in TCG or Tinecode again. Labels map directly to labels. And similarly here, we can map the addition and store to an addition and move. And then we finally branch to the exit label, and we load our results into the destination register. So the mapping between LLVM IR and Tinecode is pretty much one-to-one in most cases, and is rather easy to perform. So I want to spend a little bit of time focusing on the helper to TCG pipeline. We're going to be looking at a lot of LLVM IR, so I hope this introduction helps a little bit. So again, the point is we start from C code, we go through Clang 0 without optimization to end up with LLVM IR. We feed it through our tool, and to finally get TCG down here. Let's consider the predicated add example again from Hexagon. And this time it's written as a simple C function that can be included as a helper if you want to. We go through Clang, we end up with a lot of LLVM IR, you don't have to focus on it. The only thing you might notice is that it has the same high-level structure as the C code. You have some setup code, some branching, you have an if block and an else block, and then you return. Once we enter our tool, we firstly go through a simple like filtering phase where we remove instructions we don't care about, we remove attributes we don't care about. This is not super relevant for this talk. We then go into a simplification phase which runs a few LLVM IR passes or LVM passes and a few of our own. And this is where you start seeing the real transformations to IR. So the code has been simplified and we can now start performing a bunch of optimizations on it. So after this, we go into a small vector transformation pass. This is not something we really touch on here, but we do a bit of loop optimization ourselves and perform some loop canonicalization. After this, we go into a O3 pass, which is the bulk of the optimization. And here you can see that we ended up with an AND instruction, a comparison, addition, and a select, which is very close to what we saw previously. Afterwards, we go into an instruction combining pass that we wrote ourselves that combine, if you go back again, we take the icomp instruction and the select instruction and we combine it to a move condition. This is something that just maps easier to Tinecode. We also do a little bit of basic register allocation and such to get prettier looking IR in the end. So after this, we go into the backend, which emits the following Tinecode. And now we can see again what we saw in the beginning. We perform an addition, an AND, an addition, and a move condition. Compare this to IDF parser where we had to emit an actual branch. So what about vector instructions? Vector instructions are something that's very easy to write in C code and can often be quite annoying in Tinecode. So let's take a look at the example we saw in the beginning, performing an addition of bytes, 2 vectors of bytes. once we go through Clang to LVMIR, we end up with a lot of code, which is, again, you don't have to focus on this too thoroughly. We go into the filtering phase and then simplification. Gets a bit easier. Here it has the same high-level structure as the C code again. We see a loop header and then a loop body, which performs the addition of each element. After our small vector transformation and our loop optimizations, we end up with a bit more normalized, more normalized loop. We have extracted some induction variables. After this, we go into O3, which does the bulk of the optimization. And you can see here that we end up with a single instruction in the middle, which is a vectorized and add instruction. And this is possible due to the auto-vectorizer of LVM. So we go into inst-combine, doesn't do anything in this case. We go into the backend, which performs the mapping to TCG. And in the end, we end up with a single vectorized add instruction. So at this point, I want to spend a little bit of time showing you the actual tool and how it works. So I want to do a small demo. Oh. So we'll see how this goes. So on the left-hand side here, I have a C file. And on the right-hand side, I have an output C file. I have a small script that I wrote called, let's see if I can find it, there, run translator. It firstly runs Clang to produce LVMIR. It then runs our helper to TCG tool to produce the TCG code. So if we go back here, we have, again, our simple C file. We can just start typing. So say we want to write an add instruction. We can do, oh, I'm not super used to this keyboard. We can do something like this. If we now run our translator, which I've mapped to F, or to save actually, it should run, I think. Yeah, and we get, I think we get nothing on the right-hand side because we need to attach an attribute. So the way we do that is we add an LVM attribute, and this is how we tell our tool that this is a function that we actually care about translating. So if I typed everything correctly, looking sideways, this should work, and we should end up with some output code. Which we don't, which means I did something wrong. Typical, okay. No, the close parentheses are fine. Okay, this is interesting. I did not expect this. So what does it say here? It might not have saved, you say, okay. It should be fine. We can do this. So okay. Oh my god, okay. And then we okay. Yes, okay. There was something related to saving on the file. Thankfully. Okay, so we end up translating the file. Here we perform an addition, and we get an addition in TCG. And the thing here that's fun is we can open them both. We can say change the addition to a subtraction, which let's see if this works. Again, I set it up to do it automatically. You can see now that it maps the addition to a subtraction, which is what we expected. We can again do other interesting things, such as mapping it to, I was going to show an absolute value also. If you perform a Turner expression, it will map to an absolute value. Don't really have the time for that, sadly. I have a few other examples prepared, which are vector examples from Hexagon. Here we have an instruction that performs, again, a vectorized add of 128 bytes, but it saturates also. And in this case, LVM is clever enough to also, let's see if this works. Does it say file exists again? Yeah, okay. I guess we have to do this. Sorry. There. So for some reason I had to restart them. Okay, good editor. So we're able to map the vectorized saturated add to a single TCG gen SS add, which saturates. We have a similar example for another instruction, which, again, vector instruction iterates over all the elements. it takes the difference between the two elements of the vector and then takes the absolute value and stores that to the result element. So we're getting towards a bit more complicated instructions. I'm going to preempt this and I'm going to restart Vim. Then we run it. It runs. There. Okay, so in this case, we end up again with a bit more vector instructions. We start by performing a comparisons between the two vectors to figure out which element is smaller in each of the elements. We then perform both subtractions. We should subtract, say we have two elements A and B, we subtract A minus B and then B minus A. That's what we do in this subtraction and that subtraction. Then we perform a vectorized bit select operation to get the final result. So at this point, we can start returning to the presentation. I want to go into a bit of benchmarks, because we did want to, well, the main motivation here is to try to compare our different implementations that we have. So we have our TCG implementations produced by IDF parser, and also the ones from helper to TCG. And then we have, of course, the normal helper functions. So we want to compare these somehow. We started out by running some just normal general purpose benchmarks, which you can see right here. So the figures are the speedups relative to QEMU hexagon compiled with helper functions and a few manual overrides, manual TCG implementations for things such as loads and stores. So in this case, we see roughly 2 to 3 times speedup, which is pretty good in both cases. There's not a huge difference between IDF parser and helper to TCG. Helper to TCG is a little bit faster, but not by a long shot in this case. So here you also have to keep in mind that these are general purpose benchmarks. They don't necessarily exercise all of the hexagon instructions we emit, and we already have manual implementations for a lot of the loads and stores. So the next thing we wanted to look at is, well, okay, can we get some sort of metric on the quality of the code we emit? And here we thought of looking at the host instruction count, runtime host instruction count for a few tests. So here we're looking at a neural network test for hexagon and also a corner detection test. And the numbers you see here are the percentage reduction in instruction count compared to our baseline, which is again QEMU hexagon with helpers and a few manual overrides, manual implementations. So for IDF parser, we see a 1.5 to 3% reduction in the instruction count, and for helper to TCG, we see more like 10, 11%. So we're actually reducing the work that the computer has to do, which is pretty good. The next thing we wanted to do is we want to get a better measurement of how an individual instruction performs. And our methodology here was to auto-generate a lot of tests that try to stress a single hexagon instruction. And what you see here is there's a lot going on here, so I'll try to explain it. On the x-axis, so all of these individual dots represent a single hexagon instruction. So for instance, we see this dot and say that dot are the same instruction. The orange line is for the helpers. The blue line is for helper to TCG. On the y-axis, we have the absolute execution time. And what we can see is that, well, our blue line is mostly below the orange line, which is, ooh, good. And if we start extracting a bit more maybe interesting data, we can look at the geometric mean of the speedups, and we get roughly a 4 times speedup. If we look at these, say, peaks, like we compare, say, this instruction to this instruction, we see roughly a 30 times speedup. And keep in mind that these are individual instruction tests and can be seen as more of a, like a maximum speedup that we can expect, maybe. So, oh, yeah, okay, I mentioned this roughly. So we see an average speedup of 4 and a peak speedup of roughly 30. So at this point, I want to start rounding out the talk. So to summarize, we've created a tool called Helper to TCG. It's a build time tool relying on Clang and LLVM that's designed to take helper functions to TCG functions in an effort to help implementers, like make it easier to create a new front end. And this is primarily also a tool that is architecture independent, meaning if you have a helper function, you should be able to slap an attribute on it, run it through the tool, and get TCG code out. We applied it to hexagon, where we were able to emit at the current state, we're able to emit 1,400 instructions. The eventual goal here is to entirely replace IDEF parser, and importantly, we emit more efficient and smaller TCG code as compared to IDEF parser. And finally, we're able to handle more complicated instructions, such as vector instructions, which IDEF parser has no chance of being able to translate. And this is something that we plan to upstream, so keep an eye out if you're interested. So at this point, I just want to extend a big thank you to you all for listening, and I also really want to thank Qualcomm for sponsoring this project, and in particular, I want to thank Taylor for all of his work that he's been doing on the QHexagon front end. Thank you.
Thank you. Excellent work, by the way. So 2 quick questions.
Yeah.
You sort of glossed over, originally with the IDEF parser, you're working with the pseudo-C that's in the Hexagon architectural manual,
yep.
But this works on plain C, so how do you bridge that gap? And secondly, how much work is it to tell your LLVM stage about new TCG ops when they get added?
I didn't understand your last question. How much work is it to tell? Sorry.
So if we add a new TCG op
yeah.
to do another particular operation, how hard is it to inform your code generator that it exists and be able to integrate it and take advantage of the TCG ops?
Okay, I get it. So I'll answer your first question first. So the difference between the pseudo-C and helpers is it's not that difficult. Like the pseudo-C is close enough to just normal C that we're able to just easily bridge the gap. We have a Python script that takes the instruction definitions that we get from Qualcomm that generates either the pseudo-C or the helpers, but there's not a lot to it really. There's no real difference, you know, in terms of semantics.
Okay, well, a couple of regexes and some replacement text.
Yeah, pretty much. As for the second question, say you were to add a new TCG op, the thing with our LLVM approach is that it's very easy to just like map it to new things. Like it's easy to say, okay, if we say we have a pattern of an addition, or say we do an, so one thing we did with the MoveCon is we look for patterns of comparisons and then set cons, and then we just map that to a MoveCon. And this is very easy to do with the tools that LLVM gives us. Very straightforward.
All right, thanks.
Thanks for the great talk. When you parse the LLVM IR, like how stable is that format? Do you anticipate you're going to have to constantly chase LLVM, or will you upstream your code into LLVM perhaps?
We don't plan to upstream it into LLVM. There's a little bit of chasing that you have to do. We currently target like 4 or 5 versions of LLVM. They make a few changes every now and then to say how pointers work, which we will have to adapt to. But we'll cross that bridge when the day comes. So
okay, fair enough. Thanks.
Okay, thank you.
All right. So, modeling guest atomicity. Let's start with some definitions of, what is atomicity, and it's trying to describe how many different accesses it takes that are visible to an observer to load or store data. And the simplest is single copy when that's what we think of when we think of an atomic operation. One operation and the data is loaded or stored and nothing can separate it. And then just to complete definitions, we can talk about an operation having no atomicity, where you get no guarantees about which bytes are stored in which order, just that they're all done. And then thirdly, something in the middle, where you can only be guaranteed that 4 bytes are stored at a time, for instance, out of an 8-byte operation. This comes in trying to emulate ARM large system extensions 2, which changes the atomicity requirements of various instructions. And in looking how to implement this, I found out that TCG had no atomicity concept at all, and that things were only working by accident. In particular, the worst of it is that the slow path of the TCG memory operations uses memcopy, and libc memcopy gives us no guarantees at all about the bytes being stored. But we got away with it because the memcopy at the bottom was using small constant integers, which the optimizing compiler happened to turn into a single atomic instruction on x86 and PowerPC and other such hosts that support unaligned accesses. So in order to come up with a solution, I wanted to survey the set of guests, a set of problems that we might need to solve. Again, here's the initial the reason for doing the work was to implement ARMv4 large system extensions. What it adds to the architecture is that any access that doesn't cross a 16-byte boundary is atomic. So not moving to a cache line size, but something larger. And they redefine a couple of common instructions to provide single copy atomicity of 16 bytes. Within the same architecture, the vector extensions, which can load and store 256 bytes at a time, provide no atomicity at all. And then, because we'll still want to emulate older CPUs, we still have the single copy atomicity only with alignment. Over on x86 land, Pentium Pro, in the beginning, Intel said that only aligned accesses were atomic, and that's where AMD still stays. Pentium Pro is similar to large system extension, but within a 64-byte cache line. And then for the most part, x86 was not able to perform a 16-byte atomic access except with compare and exchange. And then the architecture was redefined. And then over in IBM land, the Power ISA changed the definition of unaligned accesses to perform stores of aligned sub-objects. So if you've got an 8-byte object with 4-byte alignment, you'll get 2 4-byte atomic stores, and similarly with 2-byte alignment, etc. And I thought I found the same wording in S390 when I first started the project, but then later I've lost track of the reference, so I can't say. So in order to handle this efficiently, we need to be able to have the guest tell us what the guest requires. And so I've put all of the different possibilities into the memory operation in bit field. And the default is the previous behavior, which is to guarantee atomicity only if the pointer happens to be aligned. And then with a within 16 to allow the operation to be atomic within the sorry. I'm sorry. I don't lost my place. Um, um, yeah. I'm sorry.
Hello. Oh, hello. Welcome to join my session. My name is Like, and I'm from China. I work for Tencent Cloud. A Chinese company behind is WeChat and other favorite games. And today I'm going to introduce you one of my side project, and it's not production ready, and called the live control of most CPU feature. Basically, we are talking about the hyper vCPU model in the data center market. And to be clear, this is one of my side project, and most of the feature is still under the pathfinding stage. And the POC is only ready for my VPMU features, and most VPM feature is work perfectly fine with my hyper vCPU mode. And I have to agree that supporting all CPU feature is a daydream. And currently, my basic change is to enable offline the first CPU, the BSP one, and enable a per CPU driver for my hyper vCPU and KVM specific eBPF scheduling. But I will not talk about the BPF schedule here. And it's not being deployed in our production environment, and most of the feature is still under Doom. And basically, my VPMU POC is just to work, and let's see how does it work. But before we move on, we just see a quick outline, and to cover the hybrid vCPU we are going to enable in the data center, and why we need the hybrid one, and how to define a hybrid vCPU, and how do we use the vCPU hybrid one to connect to the multi-VM migration pool, and how to live control using the hybrid vCPU model, and the proposal, the generic change, we want to enable it for most other CPU features, and the limitation and the drawbacks. So when we're talking about the hybrid vCPU, the stage one is we are going to enable a virtual Intel Edo Lake vCPU model, and it seems the Pico and the Eco, and there are no ISA difference, but they have different cache topological, and they are little CPU incoherency and the MSR value incoherency. Basically, I'm seeing the Pico and the Eco's capability for that is different, especially in the VPMU features. And another thing I want to mention is different between the Pico and the Eco is undefined behavior about the instruction, such as byte-wise operation and something like the shift and the multiple and the single bit shift. They are different. Be careful about the programming. And apart from the Intel vendor, and we have some AMD Pico and Eco in next few years, and we can check them follow on the AMD spec. So in the near future, we are going to see more and more hyper product in the marketing client marketing. And my point is using the hybrid vCPU model in the data center, which is not basically is not the hybrid host. And the stage two for my hybrid vCPU model, the benefit is we want to add a little ISA heterogeneity to the Pico and Eco or the other cores, just because we want to find the best fit chip for our workload, such as the AVX on the Intel P cores. And we also find an AMD pattern who is going to say we want to implement 2 ISA for the AMD product. And the stage 3 of the hyperphysical CPU model is we want to coexist all the ISA vendors such as A60 or ARM or RISC-V in one physical silicon for best fit our workload. And the Intel IDM 2-point strategy is going to say he have made a demo successfully to make the ARM x86 and RISC-V coexist. And so I'm thinking, why not we just shift left our software where emulation for the vCPU hybrid mode. The demand for the Hyper-V CPU stage 1, 2, 3 is going to, because we already have the Hyper vCPU on the marketing, and the client virtualization guys are going to enable a hybrid vCPU for the hybrid host ones. And another reason is system research. They want to pure emulations hybrid cache topology and the pure top knowledge for the research purpose. And the most interesting one is cache level is different. And the Pico shares L3, but inclusively use the L2, but the Eco shares L2 cache. And they effectively the performance, and then we want to present the true cache view for the guest so they can deploy their cache optimization strategy. And it also impacts the guest HT and cluster energetic and fault-aware scheduling. So the purpose is here is demand from the client virtualization. And another demand for data center is we want to use Hyper vCPU mode to connect multiple migration VM pool in the data centers, such as we are going to propose a common x86 to support migrate Intel VM from the Intel to the AMD platforms. And based on the basic common model, we can add or remove any interesting supported feature so that you can offline the meaningless feature and hot plug the feature you care for and after you migration to a new platform. And then you can drop the endless QEMU vCPU model version, such as the Ice Lake 1.2.6 and the Cascade 1.2.5. It's just pointless, and we can use hybrid vCPU version and add the features you just like. And another demand to use a hybrid vCPU is you want to make sure isolate a partition fault CPU. But if you fully disable it, it's just a waste. You can fully detect it and find this buggy feature, and you just doesn't use that feature. And online the buggy feature, but not touch the buggy feature one, right? And by limiting the vCPU feature being exposed, you can limit the hypervisor attack surface. This is a topic about the side channel attack and the architectural data leak and the performance attack. This is all about we want to enable the cache topological and the CPU topological in the virtualization world. So someone will say we have another solution is deploy the different CPU, different application with different capability requirements to another vCPU pool via the control panel. And my answer is if you use a virtual hybrid vCPU, the program model will be very simple and the performance will be significantly improved. And you can potentially improve your CPU utilization and reduce your infrastructure cost. Based on our demands for the Hyper-V mode, we can show me a demo, Intel Alder Lake, a virtual CPU. Basically, we are going to define a general CPU model for Pico and Eco and find the difference and define the difference. So here is the difference for the Pico and Eco. The logical number, the HT number, and the processor frequency number. Some CSP vendor do present the actual CPU frequency to the guest. And the important is the cache top knowledge and the TLB size. And from my point of view, the PMU feature on the Pico and the Eco are quite different. So I'm trying to enable the hybrid vCPU PMU feature for the hybrid guest. such as a different number of the GP counter and the top-down feature, and the Pico and equal the cache event hard-coded in the kernel driver, and the PEBS capability, and the ARC-LBR capability. Someone may not familiar with those, but more and more users are going to use a PMU feature and the hybrid PMU feature as well. And the IQ to handle the PMU events in the driver are also different from for the Pico and equal. And the good news is MSR level, we didn't find any difference on the MSR reset value on the Pico and equal, except the power features. But most guest user doesn't enable the guest power management features, right? So we can find the definition space for the hybrid vCPU. The hybrid vCPU model is just a common vCPU model based on something like cumulative topological state and the machine state, defined using the basic topological items such as code type, socket, dice, cluster, code thread. And the administrator want to use the guest topological to consistent with the current host so they can see the performance issues. And here are 3 patches to implement it. And we also want to define the KVM behavior about the emulation and the guard for different per vCPU feature. And then the most important part, you want to enlighten the guest driver to initialize this feature when the AP is bring up. So we are using the hybrid vCPU model in multiple VM pools. In the diagram, we can see there is a basic VM pool, and we have type A VM, and we hot add a type B vCPUM, and we online the type B vCPU, and the guest driver will initialize based on the online the type B vCPU and refresh his driver, and then we offline the type A feature for the CPU, and the guest driver will clean up and unregister for all type A dropped feature, and we how to remove the type A feature, and finalize we are transfer from a type A VM to a type B VM, and they are belong to the type B VM pool, and we can do this to move the type B from the type C, such as from the cascade to the ice lake to the SPR. So in detailed case, how to live control the hyper vPMU features. So first precondition is we already have the hyper PMU native support. This is because the Pico and the equal and its microarchitecture are different. So we have different PMU driver for the Pico and the equal, and we are using almost a double driver callbacks to save the function point, to hold all the callbacks, and we move it to the hot block path. And we reuse CPU hot feature to trigger our different Pico and equal vPMU features. And one of my work is we porting the Edo Lake hybrid PMU driver on the server. Basically, we are duplicate 2 PMU driver for one almost the same VCP driver, and we add a non-PMU driver when we disable the vPMU for our guest. And then we expose 2 types of vPMU as a feature representer in our guest driver. And when porting the perf tool to make it happen to support the hyper PMU on the server. And finally, we can control the guest to achieve from the PMU disable state to enable the basic PMU counter available state to enable advanced ALBR feature state. And we also support to remove feature if there is no user. So if we want to move to the Adder Lake vCPU model to the real Adder Lake machine, we want to a flexible schedule for the hybrid nature. We want to make sure the virtual Pico to run on the physical Pico. We have two solutions. First one is a hardware assistant solution, something like the Intel Thread Director. You want to dynamically detect your ISA and give it a class. And the thread director will tell you which processor is the best for your workload. And another solution is BPF extensible schedule. You ask the BPF schedule and which feature are you using, and the BPF schedule will put it into the run queue onto the target pCPU queue, right? And the helper behind the EPF program is KVM API, which basically focus on the CPU ID and MSR focus, which represent the PME feature he is using. So based on my understanding, we are going to extend the BPME approach to most CPI features. And we are just focused on the features that will be added or removed from the target migrated CPU host mode. And you can see from the cascade to iSlick and iSlick to the SPR. And I double check the feature one by one and get a rough conclusion, which is we can live control most of CPU feature based on the spec and driver review. And to be honest, it's an unprofessional quick check. And the real proposal is generic change or the shared change for live control most CPU features. The lucky one is we already have something like a hybrid PMU and a hybrid MCE and a hybrid power management in our mainstream. And the changes we need is to allow to offline the BSP CPU via the ACPI event and then remove the warning. And we are going to clean up the whole 86-baud processor and move the feature initialization to the later. And we are still going to support the kernel command line to fill out the feature users' interest and support per vCPU initialization and registration. And refresh all the callback on CPU hot paths and using the EBF scheduler to make workload adaptive migration between the vCPU. And the difficult part is we want to add more and more user-friendly knobs to enable and guest feature. And you need to fully understand the dependency of the CPU feature. And you need to customize or determine the minimum set of the CPU feature you care about. So the feature limitation, as I know, is we are not going to live control the global feature, something like the page mode, the protect mode transaction, and the APAC mode. And we are not also going to support the firmware assistant features such as SGX, TDX, and something like complicated features. And we are not also going to the synchronized operation reference to the very close related to the hardware detail. And the application migration across hybrid core should have the same view of the memory view is also the limitation. And the whole vCPU approach will break the application based on a stable constant CPU model because we are changing the CPU model identification. And online and offline, the CPU will hang for quite a long time and sometimes fall into failure. And the revert due to the offline failure will bring unnecessary trouble, and it's very hard to debug. And especially when the guests are overloaded, it's much harder to offline the vCPU and enable the features. And also the number of the pluggable vCPU is also limited by the predefined maximum topological emulation by the hypervisor. And all the tracking effort, the tracking different feature of the each vCPU add extra effort to the control panel. That's one of the drawbacks. And as a summary, I'm presenting a POC quality practice that allow VMM administrator to live control vPMU features by hot plugging or remove a class of CPUs based on a Hyper-V model, Hyper vCPU model, or to or from an enlightened guest. So rolling out from PMU feature to most CPU feature requires more case-by-case change, especially adding guest driver support on per CPU refreshment. So time-consuming and impractical to have every feature be converted. But it still makes sense for CPU feature used only at the local code scope, such as a new instruction after the line migration. And the upstream time for Hyper-V CPU stage 2 and 3 is not ready. And the application needs to gradually migrate to a new programming model, but I'm not sure if we really need that. Okay, that's all. So any questions? So basically, we are going to see a Hyper-V CPU model in the QEMU mainline for the stage 1 model. And the focus on is based on the cache topological. And my proposal is to move it to the data center world. No objection? Oh, thank you.
Hello. Yeah, there we are. So I can see how this can work for some features, like some of the ones you've described, but
Yeah.
I'm from the ARM64 background, right? But for me, it feels like most features I don't see how user space would be particularly happy. So, for example, removing an instruction, that seems like user space is going to break if it was using the instruction already, right? Like, how would you how do you checkpoint the system and say, hey, by the way, this is going away. You need to go and, I don't know, reboot, quote unquote.
Oh, reboot is unacceptable. I'm using a multi-RSA binary. Specifically, I'm using the 2 PMU interface for perf-tool.
Yeah, I mean, beyond perf though. So for example, let's say you wanted to migrate to a core that didn't have the same floating point instructions as the previous core, right?
Yeah.
To me, that seems like it's an impossible thing to do, but do you
if
you agree? Or?
If you didn't bring the important for the new feature or the new instruction, then you cannot leverage it from the new added core, right? So you have a workload ready for the new instruction and fall back to the old implementation without the new instruction, and then you get a new vCPU added, and next time you try to run the workload, and you will use the new instruction.
Okay, so how would you envisage signaling to, for example, in a running application that it no longer has the instructions that it was using before? Oh no, it's another one of these. It's not David today.
Future aware or the ISA aware workload.
Okay.
Or so actually is an enlightened guest, so it's not a legacy guest, and it's not a legacy workload, right?
Okay, so you're envisaging basically you need to change all of the software stack to be sort of tolerant of features coming and going, and there have to be some mechanism.
In my
to
POC,
find
I
that out.
also changed the firmware and the guest driver and the perf tool, just to prove if you have native Hyper something feature support in the guest, you can use a Hyper VCP model to live control your available features that you can plug in and how to remove. And some customer like to control that. So it will, I would say it will in the product. And it's a kind of a POC like just to prove the value of the Hyper VCP model in both client virtualization and the data center virtualization.
Right, thank you.
So unless there are any more questions, I think thank you.
Thank you.
Tell me when to start. Okay, ready to start? Okay. So my name's James Morse. I work in the kernel team at ARM, and wave at me if I start speaking too quickly. This presentation's about trying to support CPU hot plug in KVM guests, and I'll take the kernel bits, and Salil will talk about the VMM work. So before we get into the nitty gritty, what is this for and who wants it? It takes time to boot an operating system, so it's quicker if you're doing this a lot to pre-deploy the virtual machine and then scale them up once you know what the workload is you want to deploy. And that gives you much faster workload deployment time. You can already do this with Linux for memory, it's on ARM64, and this mechanism is for doing the same thing but with CPUs. And I've heard of Kubernetes and Kata containers wanting to do this, but I'm not really familiar with them. So there's a little bit of history and some terminology we need to agree. If you hear ARM people talking, when they say hot plug, it's typically turning a CPU off. And that's not the same as what we're talking here, because if you turn the CPU off, you can turn it back on again and keep using it. So the terminology we've got present, online means the thing's there, you can use it. Present is there, but it's not online, so you can't use it. And possible is it's not there, but it might be one day. So the version of CPU hot plug people want is initially for making CPUs that are not present when the operating system boots present, so that we can bring them online. And from a bird's eye view, the mechanism, so this thing on the right is a screenshot from the ACPI spec. There's a register for each CPU called STA, and it's got a whole load of bits that say whether it's present, whether it's enabled, and so on. And firmware can send a notification to the operating system to say it's changed something in here, and that's the mechanism that CPU hot plug uses to have CPUs come and go. So we might ask, isn't that easy? Doesn't x86 already support this? And my reading of the history is that x86 had physical CPU hot plug before it had virtualization. So for virtual machines, the problems had already been solved, and they're part of an existing specification. So on ARM, there is no hardware that does any of this, and there are new problems. So what's in the ACPI spec is not quite enough for us. So I'll pick on two. New CPUs come with new caches, and they're shared with other CPUs. And the scheduler needs to know how these caches are shared in order to place tasks efficiently. And on ARM, for ACPI, that's a static table called the PPTT, and it can't be changed once the machine's booted up. None of ARM's ACPI tables consider hot plug, because nobody's building hardware that supports it, and it's a bit of a chicken and egg problem. So we get the property that everything described in ACPI is always present. The second example is the interrupt controller. Every CPU has a gadget called the git read distributor, and those have to be found and configured during Linux's early boot. And there's a strong requirement from the IRQ chip maintainer that we're not going to bring these things online late unless there's physical hardware that needs it. So the theme of these problems is that without physical hardware, we don't know we've solved the problem properly. So adding support for a virtual machine will implicitly enable the feature on real hardware too. And once somebody builds that hardware, we'd be very upset if we found out the Red Hat installer didn't work on it, and it just panics during boot. And there was an earlier series from Salil to try and wire all this up and make it work, but it's something we really need hardware to know that we've got the spec changes and the ACPI stuff done. So are we stuck, or can we do something else? Well, the actual requirements are subtly different. So we saw this is only really for cloud orchestration. And if you take all the hardware-specific bits out of it, because it's for virtual machines, it boils down to a CPU online-offline policy, and that's something you want to control from outside the guest. But it needs to look and smell like hot plug to the guest's user space. And for the operating system in the guest, we need to know what is present, and we need that not to change under our feet. And for a virtual machine, that's not a big problem. So what we've got is allowing the VMM to toggle the ACPI enabled bit in that STA register I showed you. And that's different to the present bit, but it's in the same place. And then changing Linux so that once it sees the CPU has become enabled, so things need to be present and enabled now, it registers it, and registering is what causes things to show up in sysfs and lets user space bring it online as if it had just been added to the system and become present. And that gives us the property that everything about the system's already described in ACPI exactly as it is today, and we don't hit any of those new problems. So this is an attempt to walk through the flow with some kind of diagram. The stuff on the top half happens once during boot, and the stuff at the bottom happens every time you enable or disable a CPU. The things in yellow are events that can be triggered by firmware, and the orange blocks something that firmware has control over. So in the top left, when Linux boots, it finds all the possible CPUs from the MADT. And because we haven't defined a way of making CPUs not present, all possible CPUs are present, and Linux will then try and bring them online via PSCI, which is ARM's firmware interface for turning CPUs on and off. And that can return an error now. So that's one of the things that gets added to support this. And Linux just tolerates that returning errors because it's always been able to do that. So next, once the ACPI interpreter is ready, it registers all the online CPUs, as well as any that it finds have become enabled during the initial scan of the ACPI namespace. So from there, at runtime, so on the left, this device check is a notification from firmware that something's changed. The operating system calls STA, it notices the enable bit's been set now, and it will call CPU register. Things show up in sysfs, you get udev events to say this CPU's arrived, and it all looks like hot plug to user space. For removal, it's very similar, that's the bottom right. Again, there's a firmware notification to say, I want to eject this and take it away. The operating system can fail this if it can't turn the CPU off for some reason, but if it succeeds, There's an eject method that gets called, and then you can call STA again, and you see some of those bits have changed, and it all gets removed. You can go around that loop as many times as you like, and the initial ACPI bus scan is what makes things like kexec work to find CPUs that were changed as part of a previous life. Some of the implementation details that are now the VMM has to handle PSCI itself, because that's suddenly got some policy, and there are changes from Oliver for KVM to make that work. Remember I said there were 3 states at the beginning: online, present, and possible. As far as user space is concerned, there's now a 4th, which is enabled. And if you work on a cloud orchestrator, please get in touch if you have code that tries to inspect the kernel's present and possible masks, because those are going to start behaving funnily. There's patches to add an enabled mask as well next to them, and if we need that, we can do that. Interestingly, this should work on any architecture that uses ACPI if it can return an error for onlining CPUs. So it might be possible to get virtual CPU hot plug support on those architectures as well. And there's an RFC to support all of this on the mailing list, but Queemy is where things get more complicated, so I'll hand over to Salil for that.
Hello, can you hear me? Yeah, okay, great. So hi, let me first switch on the presentation. That helps. Sure, yeah. Hi. So just to give you an update, this is kind of a follow-up presentation to what I actually did in 2020 as part of the KVM Forum itself. So since then, some efforts have gone through in collaboration with ARM, and few challenges which were there earlier as part of the architecture mainly. We have devised a kind of workaround to get those things, not to touch those things, but then to be able to achieve what we want, which is kind of a virtual CPU hot plug, which looks and feels like a hot plug, right? So for the end user, it would be like a hot plug, but internally we are doing some sort of tweaking at different levels. I won't say all the levels, but certain, some in certain levels to achieve that end perspective. Oh, yeah. So I'll be going through the overview. It's like mostly I'll be taking the aligner in a motivation, what exactly prompted us to go into this path. Then I'll just, to set up a discussion, I'll just go for a brief anatomy, how in general any CPU initialization happens in case of the ARM within the QEMU and the KVM. And of course, the related component that is the interrupt controller for the ARM, which is GIC, how it initializes, what are the basic key elements which actually are in context to the current discussion we need to know before we actually proceed. Beside that, we need to get into the impediments again, which is kind of a recap to what we actually discussed as part of the first presentation in 2020. So I'll just give you a brief context, what were kind of a no-no from the ARM side and the entire world who actually did not want CPU architecture components to be tweaked or touched as part of the guest or the KVM host. Then there are certain workarounds around that, what we have devised, which I just mentioned. And then we'll immediately jump onto the QEMU, what exactly are the challenges and changes what we have done. So there are certain problems I've objectivized in terms of, say, 1, 2, 3, 4, 5 problems, which depends upon the kind of design technique what we have taken to get around with the limitations posed by the architecture at both fronts, that is the guest kernel as well as the KVM host. So yeah, so in a quick replay, the motivation is basically, as you all understand, this is much vouched featured by the cloud vendors, and they require it as part of the orchestration framework of theirs. And generally the use case is to adjust their resources, which are primarily, in our case, the CPU and the memory dynamically. And it could be based upon the usage. For example, it could be a very much dynamic scenario in which certain resources are underutilized, and then you want to pull it out from the VM, which is, say, for part of some sort of a containers or pods, as you call it as, In that case, you don't want to have that kind of vCPUs allocated to them. So that's a dynamic kind of usage. Other usage could be a long term. For example, it could be related to business model in which a customer starts with some sort of a small scale businesses initially, and then basically as it grows its business, eventually it ends up in some sort of a, it acquires a higher kind of hardware which is much more capable. So it might be the case in which the end user might request more resources, which he should be allowed to take. In that case, you require a similar kind of feature to be plugged in. So the other thing is like one of the key requirement is the look and feel of the x86. So because the end customer who are the cloud vendors, they don't want to change their the scripts and number of other things, and of course there's a lot of a training time with respect to these kind of things as well. So what they want to do is just whatever you get in x86, they exactly want to map into the 64. One of the examples of this is the Kata container. As I said, the basic approach for them is basically hot plug everything at the start. Why? Because they want a faster boot time, and then decide basically how many resources they want to plug in. So that's a hot plug, right? For the CPU, that is what we want. So I'll just quickly get over with the terminology. That is from the ACPI perspective. So there are three possible states what we see in the CPUs right now as possible, present, and enabled. And enabled is something which we have introduced very recently, but yes, I'll just discuss in the coming slides. So possible is like what is the maximum possible vCPUs that can exist within the VM in its lifetime. You cannot change that, you cannot tweak that, that's fixed once and for all. The present vCPUs is something which is present, but they need to be enabled, right? And they actually cannot be used. And this is what we are trying to expose as part of the vCPU hot plug kind of look and feel to the guest. The other part is the enabled CPUs. That means eventually they have been enabled as part of certain action which has been done within the VMM or the QEMU. And that has resulted in some sort of handshakes between the guest and the VMM, which resulted in onlining of that particular CPU, which effectively means that some PSCI calls, which are related to power management or power state coordination in the ARM, they actually enable that vCPU, and it comes out from that low power state to the actual state, right? So the brief anatomy, just to set up a quick context to the actual hot plug. So this is without hot plug. These are basic things which happens at 40,000 feet, I would say. Well, you create a CPU basically within the VM. So when the VM ends, basically you end up in creating some sort of a CPU object, which is nothing but a representation of a CPU within the QM. That is a QEMU object model, and that ends up in some sort of per CPU initialization within the QEMU, and also results in some sort of a calls to the KVM that happens during the realization phase, and that results in like some sort of a creation of the vCPU within the KVM. So there's a separate context for each vCPU which gets initialized within the KVM as well. And these are, of course, again, the per CPU vCPU context, and they also initialize some sort of per CPU features like timers, PMU, debug, etc. And of course, some sort of interrupt initialization, which are per CPU, like all the private interrupts, what we see SGIs and PPIs. And of course, in the end, you have to run that CPU because you want to use them. Then, of course, there's a KVM run call. All of this right now happens with respect to whenever the thread realization of the QEMU happens. And basically, you're up and running, but not so quick. There's a ARM GAC initialization which you have to do as well. So you have to primarily, the things what we need to take care of is the base addresses what need to be initialized as part of the QEMU, and basically there are certain IO devs in the memory regions which gets initialized as part of the redistributors. That those regions are something which are which gets mapped on some sort of registers, whether they are system registers or related to a GIG-D or GIG-R or CPU interfaces inside the KVM. So what are the impediments? Let's get into that very quickly. These are a recap of the earlier presentation. So just two in broad sense, basically number of CPUs, right? I talked about the possible CPUs in the system which can exist. So basically this is a red line in terms of the CPU architecture. You just cannot manipulate with the CPUs, right? So then the question arises, how would you realize the hot plug, right? That's a question we are going to answer, right? We are trying to do some sort of I would say creative hacks, if I can put it, as to just get around with these things. And other thing is the sizing of the VGIC or the GIC. So this is again the architecture constraint which has been imposed. You just cannot reinitialize the GIC or uninitialize and reinitialize certain part of the components. It has to be done in whole at the init once and for all, and that remains for the VM lifetime. And then the other part is, yeah, sure. Other part is the association, which remains like the association with the VGIC and the redistributor. So yeah, so the same thing happens with the guest kernel, which is like the same kind of constraints are there in the CPUs, redistributors, and the associations. So we cannot change any of these. These are like red lines. So getting into the workarounds, it's like there's no workaround at all in case of the KVM host as well as the guest kernel. We actually have to get everything the way they are, right? So memory regions, everything gets initialized the way they are expected. The only thing we are tweaking right now is the power state. So with respect to the guest kernel, the same thing, whatever the constraints from the architecture point of view I just talked about, that will remain the same. We cannot touch that. So what we can do and what we have to do, because there's some sort of changes we have to do. So there's something like currently, because whatever gets described as part of the ACPI MADT as part of the GIC CPU interface, right now, just before this change, they had to remain always present. Right now, that change is still there. I mean, CPUs will remain present always because that is a constraint, right? But then how would you make it present, or I mean, in a other sense, that how would you plug and unplug in the guest? Basically, there's another bit called as enable bit, right? That comes as part of the status. We tweak that particular bit to enable or disable that particular thing. But this was also not allowed as part of the earlier changes. So there are certain changes related to online capable bit, which has been added as part of the MADT table, which just states that whether this is allowed, whether the CPU which is coming up can be online later on after the OS has been booted. So that is a key change in the guest kernel. Okay, sure. So this is the base 3 levels. So to cut the long story short, is like we fully realize the vCPUs, and we basically just toggle the present and the enable bits, and we fake all of the hot plug at the QM object level, and we lie to the guest about the presence of the CPUs. So that is the key. So second part is what I'm going to cover very quickly, right? So what are the challenges, what we have? The challenges is like, of course, the look and feel of the vCPU hot plug, what we have, right? We cannot change, or we cannot, we have to use the same set of interfaces. What actually that means? That means the CPU objects which are getting created as part of this, somehow we need to fit into the existing initialized components, which means that, for example, GIC has got its own CPU interface state. It gets attached to some sort of an older CPU, right? CPU object, I would say here. But that gets deleted as part of the unplug action, right? At the QM level, right? So we have to do some sort of a tweak basically to reattach them as part of this, the QEMU changes. So that is what we are doing. But even before the hot plug, the initialization is important, right? So the key thing is, how do we initialize the entire set of possible CPUs now? So there's a key set, but a subtle difference. So now initially everything was being initialized, had a kind of a realization in a QEMU sense. Everything was present, was realized. Now actually we end up creating ARM CPU objects for entire possible CPUs, but only realize, that is, QEMU threads are present only for the objects which are actually plugged in, right? So the vCPUs which are not plugged in doesn't have the realization part, and they are only used for the KVM population. So once the KVM is populated with entire vCPUs. That was the requirement, if you remember. I just told you that that's a CPU, the architecture constraint. We just end up in destroying those extra CPU objects what were created as part of this initialization, right? And then we again, so these slots are empty right now, and whenever the hot plug action happens, basically we have to again bring them back and attach them and fix them in the same slots. But then we need some sort of a tweaking in the gig. So gig has been fully realized because that's part of the architecture constraint, right? So what we do is there's certain updates we have to give it to the gig as part of that hot plug action which happens, which actually ties up that CPU, which is new CPU coming up, and actually updates that gig CPU interface, which has already been realized as part of the gig initialization, which has to happen as part of the QM model, right? So this is precisely what we are doing. But there are certain impediments in this, like as part of the init access operations and the updates, there are certain things we have to take care of. I'll just quickly jump onto those. These are like some subtle changes. Say, for example, realization, right? Now, we only assign the CPU states to the one. Remember, I just told the threads are only for the plugged-in CPUs. So basically, we need to fix in this particular state of the gig, right? So whenever a new CPU comes into picture, KVM has got every state fixed in. It's just the QEMU model we are fixing in. So basically, we attach this particular new CPU to this state or unattach it, depending on what action is being done. Then, of course, there are certain register information which we need to reinstate if you destroy the CPU object, which is peculiar to QEMU because when you reset the CPU, for example, there's some sort of a handling we have to do in case of the QEMU. What is that reset handling? That we have to reset the get CPU interfaces as well, right? So whenever you get such kind of event, you have to handle that. So for that, you need some sort of a co-processor registration. So you have to redefine those registers which are not being handled by the KVM. So those kind of things we have to reinstate. And the other part is, so it's related to the presence of the CPUs within the guest. I think I briefly discussed earlier, we are making use of the present and the enable bits. So basically present will always remain as present, but enabled is something what we can tweak in, right? And for that we have done some sort of a ACPI change. There's some sort of bit which has been introduced, which makes a certain CPUs online capable. That means in deferred online, right? So that means entire OS or VM has come up, and we are actually allowed to basically, as part of the QEMU actions, set these particular enable bits on and off. So we are kind of faking to the guest that something is now present, though actually as part of the QEMU object model, these are not present. So that is a bit of a contradiction with respect to the actual presence of the CPUs in the guest as well as the KVM host. So one last thing is like, eventually, okay, so you have everything in place, but there's a key problem is like compatibility across different kind of releases. So which might or might not have virtual CPU hot plug, and to be very frank, we cannot deny the presence of physical CPU hot plug in the future systems, right? And what if both of them exist in future, right? So we should be able to distinguish these three cases, and all of these are in individual, they should be able to exist. So what exactly we are doing is we are making use of the OSC call from the guest kernel, and which ends up in the VMM, that is the QEMU. We evaluate that, and eventually we give the right answer, what exactly is the compatibility. And that leads to either denying those actions happening in the user space or just happening. So there's one more change which is not part of the slide, is actually the PCI aspect, which is related to security. We also, while onlining the CPUs which are coming up, we also check whether these are actually allowed as per the policy within the QEMU. So there's a VMM policy decision which is also involved in it, and that particular gives you a deny or let that CPU be online. So that's a basic simple concept what we have tried to kind of prototype. So yeah, so the prototype code right now is present as like at these latest QEMU and the kernel repositories. You can try, they work. It's not like a perfect code, it's a prototype. I would say it's a kind of a hack, but then you would agree that there's a very thin red line between the bravery and the madness, a bug or a feature, or a hack or creativity. Let's call it a creative hack, I would say. So acknowledgements to a lot of people involved because there was a lot of discussions. This is a work of mutual interest and have been going for past 3 years. Thank you so much, and I can take some questions if you wish.
Is anyone going to use this if we support it?
Use it. That's it. Anything for James, maybe? Yeah. Mark has got questions, I think. Or the will. Yeah, sure, Alex. There you go.
So how long has this taken from the first initial implementation to getting to where we are now?
So to this point, you mean to say? So we, actually, I started with something like in January 2021, to be very frank, the first prototype. And it took roughly 3 months to get kernel and QEMU part both. And the patches were floated in June in 2021. But I think, of course, there were objections, which were well known because there were previous attempts as well. And then there was kind of a blank in between because things were being discussed as part of the architecture team. James did quite a good work. Jan Philip from ARM and Linaro, depending on what time we are talking, because it's a long time. So they did all that work of at the background while we were having a discussion in a common platform that is a Linaro open discussions. I think where a lot of people came in and gave their point of views. And I mean, we had different approaches as well from the ARM, especially from the kernel, thanks to everyone involved in that. So earlier so there were some impediments in those approaches. So something couldn't be realized at that time. In 2021 itself, we could have had a similar kind of solution. But then because of the changes in the standards, which were not allowed for those particular states, so we just didn't go in that area. But then some more changes, like for example, enabled and present bits, like we have to have that online capable bit, right? For that, we had to wait for the standard change again. So that took a bit of time. So it's like a small things which took time. And then eventually something we could present and say that, okay, you can use it. Yeah. So conceptually, it's very simple. We are not doing anything funky except within the QEMU, because QEMU changes are disruptive. What we are doing is anti-model and anti-architecture in a lot of places. Like for example, Mark also pointed out in the patches what I shared. In terms of the architecture, there's no difference between the GIG CPU interface, right, and basically the CPU itself. So basically they are together, right? So, but the QEMU changes actually assumes that while we unplug the object, CPU object from the QEM, right, we actually delete the state, right? So that state still exists partly within the GIG CPU interfaces, which is already realized. So we have to reconnect from the QEMU point of view that particular state into the realized state. So, which is not very clean, but it works because it's not affecting the offloaded state of the KVM of the CPU interface. We are not touching that part. So yeah, I mean, like other than that, I mean, like there are things which, for example, the initialization of the entire possible CPUs, right? If you see, so there are certain things like certain CPUs which are unplugged, right? So we take a kind of it's again, I would say it's a kind of a deviation. So we don't deviation from the QEMU itself, because QEMU doesn't have any kind of state which is not realized, right? So you create an object that ends up in that set realized call, and that with respect to the CPU, it ends up in spawning that QEMU thread as well, with respect to the initialization, what happens. But we are kind of hindering that, we are stopping that particular part. Why? Because we don't need it as part of the unplugged CPUs, because that is, and there are certain things which happens with respect to that calls, which is like the creation of the CPU and the initialization of the CPU, right? And those things, we have to do it separately just for the sake of the unplugged, right? So the things which are happening for the normal sake, we are not doing for the unplugged CPUs, but some of the things we are doing as well. So the thing what we are not doing is a KVM run. Okay. So I think, yeah, so maybe you guys can try and let us know what exactly how it looks like. But there could be, there's a disclaimer that there could be bugs definitely over there, and could be problems as well.
Okay, thank you.
Hello, everyone. Welcome to the last talk of this year's KVM Forum. I hope you are not too tired, and thank you for everybody who stayed for that long. So I'm trying to talk a bit about CPU models, and basically this is supposed to be more like a problem statement kind of talk. I don't have really any solutions, and anybody who has looked into the problem of CPU models won't be surprised, I guess. So what do I want to talk about right now? So what's the actual state, which is, yeah, confusing? And what do we actually need? So what has prompted this is basically everybody wants CPU models on all architectures, and on ARM it's a bit difficult. And I'm trying to, and the last one is I'm trying to come up with some ideas of what we actually want to do. But I don't have any solutions, and what I really want is that we can discuss things and maybe rule out stuff that won't work at all, and maybe just start the discussion, which can, of course, continue and will continue, I guess, later on. So where are we right now? So if we look at the different accelerators for TCG, we basically have named CPU models. You can say, hey, I want a Cortex whatever, I want a Neoverse, and there are various types available. And if you just start your QEMU with the CPU model, you will end with something that is reasonably accurate to the model you actually specified. The other option is the max CPU model, where you just go ahead and let's just emulate everything that exists and just give it a go with everything that's new and cool and so on. For KVM, it's a bit more difficult. We also have a max CPU model, which is basically the host CPU model. So basically we look what does the host do, and we try to enable this if we have the code available and we know about the features and so on and so on. We also have named CPU models, which are not that useful because you would need a host that is actually matching whatever is in the model 100%. And good luck finding a CPU which actually matches. We have also a bunch of CPU properties which you can explicitly specify when you are trying to initialize your CPU. There are various categories. So you have some properties that match one-on-one to an ARM CPU feature. This is very obvious what this does. Then you have some TCG specific stuff, and then you have some KVM specific stuff. This is mostly, at least in the KVM case, it has mostly been introduced to be able to deal with older versions of KVM. And what do we actually need? Because we don't currently have really much on the ARM side. If you compare this to other architectures, they have a much richer feature set where you can switch, for example, CPU properties on off. You have something like CPU model expansion, which also exists, of course, for ARM because it's a generic feature, but it's not that useful. What I think we really need is basically we are defining a CPU. If we have this, we specify I want a CPU with this and that, and then we want to have a reproducible thing. So if you have a newer QEMU, if we have a slightly different setup, we still want to get the same CPU and not something which is similar just because we end up with a newer CPU, with a newer code level, and then you just have new stuff there. And then you are wondering suddenly, why does your guest see features that didn't exist before, or why does it behave differently? This is, I don't think anybody desires that. We also have new features coming up all the time. We also want to be able to just use them quite easily and not to need to write a lot of boilerplate code just to get all of this going, especially if you consider higher level administration interfaces like libvirt. Then we don't want different accelerators to be completely different. So if we have a command line that works with KVM, it shouldn't be something completely different on TCG or on any other accelerator we might want to use. And last but not least, a management interface like libvirt also needs to be able to actually find out what is supported on the platform. So it can say, okay, I'm spinning up a VM, and this is what my system currently supports, and not just try it, and if it doesn't work, then we'll just try again. That's not a good use case. Compatibility handling is probably one of the more fun parts, especially if you consider live migration. If sometimes you will need to migrate a system from an older version to a newer version, and you don't want to see any change in the guest for those migrations. And for this, we really need to have something that is actually reproducible. So like say, hey, we want a CPU with those and those features, and then we have a newer version and have the same CPU, and it just does not look any different in the end. And yeah, the other thing we use for compatibility in QEMU is, of course, compat machines, and those compat machines might have some intersection there. I've seen it on other architectures like SV90. They have intersections with whatever, like you have the compat machine and then you are doing some feature bit fiddling for the CPU so that we end up with the same thing in the end. And we might want something similar on ARM as well. And but what I think we need to do, we just need to limit ourselves. If we look at the ARM ecosystem, the CPUs that are available are just really different. You cannot just pick a random CPU and then expect to be able to migrate to something which is completely different. This won't work at all. You'll just go crazy if you try to do that. And that's also a difference like to other architectures. So x86 is, yeah, it's also quite heterogeneous. SV90 is better, but even on SV90, we have variability, and ARM is just far out to the right if you look at it like that. And we also, if we want to have something cross-hypervisor, we also need to consider what the accelerators need to do. TCG is simple because TCG, we control what we actually do because we are doing it all ourselves. But for KVM, we also need some support in the kernel, like, hey, we don't want this feature bit. And I mean, there's a patch set currently on the list, which is trying to make this accessible to user space so that we actually can configure some stuff. And this is going in the right direction, I guess. So this is something we will definitely need in the future. And I want, maybe this is probably the most horrible thing. I see a lot of nodding here. We do not really, we have errata all the time, we have changes all the time, which are not really architecture-wise. We have some really, we could have some CPUs which look the same on the surface, but in the end they are behaving differently. And this is probably the worst nightmare. And there's also the question, what should TCG do? Should TCG just ignore all of that stuff and say, okay, we are just sane, we are TCG, so we can do sane stuff and don't need to worry about what real hardware is doing. That's probably the easier approach, but yeah. And how can we actually move forward here? So the problem is, how do we actually name our CPU models? If we agree that somebody firing up their system, they want a CPU with a certain feature set. In many cases, they know, okay, I am running on a whatever, Cortex, whatever, and I want a Cortex, whatever. And if I'm using TCG, I'm just doing right that I'm saying, hey, give me that Cortex, whatever. This is the problem with this is it's not easy, it's not really scalable into the future, and it's also not really scalable across the many versions of CPUs that exist and the many CPU vendors that exist and the many boards where people put CPUs in and all that kind of stuff. It would mean we would need to patch QEMU for every new CPU that comes along, and this does not scale at all. Using architecture revisions would be another options, like, hey, I want an 8.6 CPU with the following optional features. This fails if we are trying to consider KVM because we cannot really reliably figure out what is the CPU. We might not know what architecture level is this actually. We might guess, but we may be completely wrong if everything comes just in the right places. Well, I think we need to go with the Frankenmonster CPU. It's basically build your own. It might look like a real CPU that actually exists, but we will just try to figure out on KVM basically what does the host do, build a CPU model that basically is the intersection of what the host does, what our software does, and assign it a UID. And then if we know how to construct it, we can also construct it, for example, on the destination host if we are doing migration and build something there. And I mean, for TCG, you can also go ahead and say, oh, I want this really weird CPU that doesn't exist in the wild, but I'm just building it anyway and just assign a UID, and there you have with your very weird CPU. The other thing is currently there's a lot of properties that are not configurable from the QEMU command line. We have set, I think it's like 10 kinds of properties where we can actually configure something, and more if you have, for example, different vector lengths. But it's really not much. If you look at typical POC CPU info in Linux, you see many more variations of features, especially if you look at one of the newer hosts. They have a real zoo features they expose. And if it shows up in POC CPU info, we know that the guest knows about it. So if we want to ensure compatibility, we need to be able to actually configure it so that the guest isn't suddenly surprised that something is there but that wasn't there, or the other way around, which is probably worse. So basically, as I wrote here, if it's something guest supportable that may differ, we must be able to actually configure it, or we cannot support the compatibility between those two CPUs. And I listed more of this, and it's basically, if we look at it, you are going crazy. Just look at the features that are supported in ARM revisions, that features that are added, the combinations that might be possible in the wild. Yeah, it means we really need to limit ourselves, because otherwise it is just a support nightmare. Then we have obviously the big difference between TCG, where we are in control. Basically, the CPU does what we have programmed it to do. And for KVM, we have the real CPU on the host. We know we need to consider what this is doing. And we also need to consider what the various software levels are doing. Like, you have a new version of KVM, which has gained some new cool features, and suddenly everything looks different in the host, which is also, yeah, features added is mostly not that bad, but features removal, if you migrate to a different version, is probably not something we want. And also, we don't want to present users with too much required choice. Basically, we want to wait for them to tell, hey, I want a reasonable CPU which runs on this generation and is just reasonably well matching whatever my current host is doing, and just give it to me and don't bother me with any details. And the other thing is, of course, of the configuring, that libvirt needs to be able to figure out what can we actually tell QEMU to configure. And of course, these are not the only open questions. These are just some open questions. And I could probably have added some more slides with open questions, and you will be probably telling me more open questions. It's basically, how flexible do we want this to be? Do we want to have really weird Frankenmonster CPUs that can be anything weird, which will never exist in the wild, like combining wildly different architecture levels and stuff like that? Or do we just want to say, okay, you want this, but this is too crazy, don't do that? And also, what level of compatibility do we want between different systems? Do we want something like just, oh, there might be some minor difference between those two hosts and we want to migrate it, so we just need to be able to configure some slight differences, and then we can just seamlessly migrate it, which looks way more doable, like than I have here this Graviton and I want to migrate to this Ampere, which is just insane, probably. And also, what do we actually want to expose? Can something be hidden? Can we be a bit closing over things, because in reality it doesn't matter, and implementing it would be much more trouble than it would be actually worth in the end? That's another question. So now that we have so many open questions, I guess many people in here also have more open questions and comments, and because I also already saw people smiling, nodding, so maybe let's open it for questions now.
So the errata issue is something that we've put a lot of thought in with managing ARM machines in GCE. And I think the one unfortunate reality is no matter what you do, the guest is painfully aware of whatever misfeatures exist on that system. So I think maybe one way to go about it wouldn't be to hide that detail from them, and in fact, report to the guest what your schedule, the pool of machines is that you support. Like that might be one way around it, but to say that a certain implementation behaves exactly the same on another system is seemingly playing with fire. Yeah.
There is a problem with the errata. Like I don't know anything about ARM, but I spent like 10 years thinking about features on x86. So there are some lessons learned. The problem with the errata is that you don't know that they exist until they are discovered. So basically they are, you can have a bit, but it doesn't tell you what works. It tells you what doesn't work. And all the machines that you have running until that point, you cannot teach them about the new errata because they don't have the kernel, the new kernel, or they don't, even worse, maybe they have the kernel that knows about the errata, but it doesn't have the bit because it was started without. I don't know if ARM has features that were removed and they added a bit to tell you that the feature is not there anymore. God, I mean, how do you know that it that it might disappear in the future? So errata is basically a negative feature. There's no hope of fixing it.
Yeah, negative features are just nightmare, I guess.
And the problem there, though, is like it's not even described in the feature registers that actually describe the architectural feature set of the system. It's mostly discovered based off of the MIDR of the system.
So we do have negative features. So you know a bit of I mean, it's worse than that because there's a you can basically do anything you want with the architecture as long as you pay some money. And for example, you can have a PMU of some revision, but you can also have an implementation defined PMU which doesn't follow any of the rules that are contained in the architecture. And the way you indicate it is by having something that says, it's not that I don't have a PMU, I have a negative PMU. It's actually a signed value. It says -1. It says, no way, I don't have that. I mean, I have something that you can't make use of. So we have this spectrum of not only of revisions of particular feature, but also sometimes something that becomes negative. Tell you no, actually it's gone. So obviously you can't. I mean, these two implementations are not compatible. If you want to migrate between these two, too bad, you've lost. So I've worked on some vague idea where, because the architecture gives you a way to specify a synthetic MIDR that says this is a software implementation of a CPU. And what I came up with is not very good, but that's what I have at the moment, which is basically I tell you this: you have a software revision of the of a CPU, and here's a firmware call that will describe all the possible revisions of implementations you can run on. Go and implement all the workarounds you can, and if you have conflicting workarounds, tough luck. You can't run. But it's I mean, nothing's perfect there. It's basically broken by design, by flexibility, and if you think ARM is bad, think what RISC-V will be 5 years from now, because that will be even worse.
So should we basically consider, hey, we have some kind of QEMU CPUs which are like the real CPUs but just close enough?
So the one thing that I kind of worry about is, so I guess my background, I come from the Google Cloud side, so don't really expect a lot of influence over the guest kernel and anything. And these sort of like KVM specific or QEMU specific like PV interfaces are kind of terrifying to me because it doesn't mean anything for the customers that are unaware of it. So I think if we were to go in a direction like that, we might want to get something architected for it.
Yeah, it would need to be architected. We can't just define our own. I mean, I have a prototype, it's nice, it's fancy, but on its own, it means nothing. It has to be architected, it has to be supported in actual revision of some VM firmware, and it has to be universally adopted. So it means that Hyper-V should also, for example, be able to expose these things.
Don't just say yes or no. Tell me how naive it is. Has anybody tried talking to Microsoft about this?
Not personally. I don't have any direct contact with them. But I think that's why we have ARM. I mean, that's their job, really. I mean, we can ask them to yeah. Well, I think it's more than just individual companies. I think it's as a community. If we want ARM VMs to be in a better shape when it comes to live migration across implementations, then we need something that is consistent, and the right place to define that is at the architecture level. So that's, for me, that falls directly onto ARM's plate. To do. It's not the first time I mentioned these sort of things.
So one more question for me that I just thought of. Do we have any lessons learned from other architecture CPU models where you say, whatever you do, ARM, don't do that, just never do that? Any good advice there?
Well, negative features like behave as if they don't exist. Like, don't even bother exposing them to the guests. So the kernel has to do something sensible. Like, tell the guests that every old obsolete feature exists, because if it's obsolete, nobody's using it anyway.
I guess just a little bit of a news update, since you had mentioned it earlier. The KVM series that you were talking about to allow configurable ID registers was merged an hour ago. So, but I think Mark had a really good suggestion on how to improve it for user space too.
Yes. So from what I understood, you want to have some sort of interface that tells you not only what the host supports, but also what are the bits that can be modified.
Exactly.
Yeah, so I think we can probably help with that. So the way with that patch series, you've seen the way the ID registers are managed. So they are mostly read-only at the moment, even if we allow people to write to them. But because they are segmented in fields, we track internally which fields are actually writable. So one possibility would be to expose the masks that describe which fields are writable to user space, so that you could discover that, and there would be, each mask would be associated with one field in an ID register, and that gives you the features that would be available to modify.
So I think with that, the default value in KVM for all these fields would describe it at the maximally supported feature set. So effectively, it would become a mask of features that user space could negate, actually. Or downgrade, yeah.
So you may have just answered it. So does every feature that's advertised in the ID register come with a corresponding knob that the hypervisor can turn off to disable it? But having a writable feature bit implies that the hypervisor can do something about it.
I can move as well. So it means that the hypervisor can do something about the value. It doesn't necessarily mean you can disable it. There are some features where the architecture mandates that it's there, but you have various level of support. So we could say, okay, you can't turn it off, but you could go back to the basic level of support. Or at least we don't advertise it. For some features, we just can't disable them, but we can stop advertising them.
That's not too far off from the x86 model too, though, right? It's like a lot of like the user space visible features. There's no controls to turn it off in VMX, nor is there for EL2 on ARM. It's kind of on the good intentions of the guests that it doesn't actually use a lot of those user space visible features.
it's not necessarily written anywhere that an undefined opcode actually raises an exception. Sometimes it can just do what it's supposed to do in later releases.
The architecture is pretty precise in this department, and it says that it will most often result in an undefined. it will undefined.
There's a certain probability that you're running bare metal or in a virtual machine. Most often you're running on bare metal, it does an exception. If you happen to be running on a virtual machine, maybe it doesn't. No, apart from that, one suggestion is do not just think of what the API looks like, think of what the documentation looks like, because these things are a nightmare to document. So make sure that you also teach the VMMs what to do with your API.
So if we were going down that road, my plan would be to report something that has exactly the same format as the ID register, at which point I point you to the arm and say, that's what it is. So I mean, I'm convinced that if you want to specify the shape of a vCPU, you will eventually have to specify all these 56 ID registers, all of them. I don't see another way.
I think that the KVM documentation starts and ends with how the ID register interface interacts with our existing feature configuration model. Like we have like the feature flags. I think that would be really important to document because it does have weird quirks about it. But otherwise, in terms of what's strictly described by the architecture, I think it's best that we just give it to the arm. I think that's a question too.
Just an example for x86, we have some bits that we later realize they don't depend on the hypervisor. User space can always set them. But maybe if you have an older hypervisor, it's not set. So some bits the user space knows it can always set. Some bits you can always set if you have a certain capability. Some bits you can always set if you enable a capability. So it's not just that you have a documentation of what the bits in IDR do. It's basically how the features interact with other parts of the hypervisor. So these are kind of quirky things that are going to happen.
Yeah, so I think what we also need, Alex, you're sorry, I don't. Sorry, I didn't. Yeah. So I think what we also need to consider is that libvirt is. I think they are really hot on you get what you define, and if you say the same, you want the same thing, you get the same thing. So if something can change, we probably need to expose it to libvirt so they can configure it and build whatever they need on Flex and so on.
Not about the CPU models. So we have to basically turn off the audio, video, streaming, everything. But we still have some time, like 1 hour, like yesterday, until 6 p.m. So we can continue this as a kind of impromptu buff. Sorry for hijacking.